tonight, we're drifting into one of the grandest beginnings in all of astronomy. We're going to explore what really happens when galaxies first form, not the quick version, not the neat textbook summary where clouds collapse, stars appear, and a tidy spiral galaxy politely poses for a telescope photo. Real beginnings are rarely so organised. They are slower, messier, stranger, and far more interesting than the polished images suggest. Long before graceful spirals stretched their arms across space, long before bright city-like clusters of stars decorated the dark, the universe had to learn how to gather itself. Imagine trying to build an entire continent out of mist. That is not far from the challenge. Galaxies are among the largest organised structures in nature. They contain stars by the billions, gas by the trillions of tons, dust, planets, black holes, magnetic fields, wandering comets, violent explosions, quiet nurseries, and ancient light still travelling outward from places that no longer look the way they once did. Yet every one of these colossal systems began from something subtle, a slight unevenness, a faint advantage in density, a patient pull of gravity repeated over immense spans of time. If you think about it, that may be one of the universe's favourite habits. It takes tiny differences and gives them enough time to become mountains. Before we settle in fully, I'd love to know where in the world you're listening from tonight. Are you under a city sky where only the brightest stars manage to peek through? Are you somewhere rural where the Milky Way still spills overhead like frost? And what hour has found you? Late evening? Early morning? Somewhere in between? It feels fitting to ask, because while we speak about the first galaxies, each of us is listening from our own small point in space and our own moment in time. If you find this soothing, interesting, or simply a pleasant way to unwind, I'd be ever so grateful if you gave the video a like, maybe subscribed, and joined this little corner of calm curiosity. It helps more fellow night travellers find their way here. Now, get comfortable. Let your shoulders unclench. Let your breathing do what it already knows how to do. There is no rush where we're going. The first galaxies certainly did not hurry, and neither shall we. To understand how galaxies form, we need to begin in a universe that had none. There was a time when no stars shone anywhere, no galaxies spun, no planets circled suns, no glowing nebulae decorated space, no black silhouettes of dust crossed bright stellar backgrounds. If you had somehow looked around then, you would not have seen the rich cosmic landscape we know today. You would have found something simpler, hotter, and astonishingly uniform. After the Big Bang, the universe expanded rapidly and cooled. In its earliest moments, conditions were too extreme for atoms to exist. Matter was not arranged into familiar things. It was a dense, energetic plasma of particles and radiation, tightly coupled in a brilliant fog. Light could not travel freely because it constantly scattered off charged particles. The cosmos was less like empty space and more like being inside a glowing, endless interior where nothing could be clearly seen. Only later, when the universe cooled enough for electrons to join nuclei and form neutral atoms, did that fog begin to lift. Light was finally able to stream across space. We still detect that ancient light today as the cosmic microwave background, a faint afterglow that reaches us from every direction. It is one of the oldest photographs possible, though photograph may be too neat a word for something taken by physics itself. What that relic light reveals is remarkable. The early universe was smooth, not perfectly smooth, but very nearly so. Temperature differences were tiny, density differences were tiny. If you compare one region to another, the variations were measured in mere fractions, and yet those fractions mattered. Suppose you laid a vast sheet across a table and sprinkled flour almost evenly over it. Almost. Here and there, a few grains land slightly thicker than elsewhere. At first glance, it looks uniform. But if gravity could act on those extra grains for millions and billions of years, the thicker places would gain more, and the thinner places would lose by comparison. The smallest imbalance would slowly become structure. That is essentially what happened. The early universe contained minute irregularities. Some regions were just a little denser than others, not dramatic lumps, barely noticeable preferences. But gravity is famously patient. It does not need drama, it needs time. Where matter was slightly denser, gravity pulled a bit more strongly. That stronger pull attracted nearby matter. As more matter arrived, gravity strengthened further, which drew in still more matter. This feedback process continued again and again. Places with a tiny head start became gathering points. It is tempting to imagine galaxy formation as a sudden collapse, but reality is closer to a slow negotiation between expansion and attraction. Space itself was expanding, carrying matter outward on large scales. Gravity, meanwhile, was trying to gather matter inward where density allowed. One force stretching the map, another trying to collect pieces on it. For long ages, neither side won cleanly. And there was another major player in the story, one that cannot be seen directly at all. Dark matter. The name sounds theatrical, but astronomers use it quite practically. Dark matter appears to be a form of matter that does not emit, absorb, or reflect light. We do not observe it with telescopes in the usual sense. We infer its presence through gravity. Galaxies rotate too quickly, clusters behave too strongly, and cosmic structures form too effectively to be explained by visible matter alone. In the young universe, dark matter was crucial. Ordinary matter, the kind made of protons, neutrons, electrons, atoms, gas, stars, and you, interacted strongly with radiation early on. It was pushed around, heated, and slowed by the energetic environment. Dark matter, however, didn't couple to light in the same way. It could begin clumping under gravity earlier and more efficiently. That means before normal matter-formed stars or galaxies, dark matter was already assembling invisible scaffolding. Think of construction workers arriving at a site where no walls exist yet, but steel frames are quietly being erected in the fog. Later, concrete, wiring, windows and rooms will follow those frames. In cosmic terms, gas would later fall into these dark matter halos, using them as gravitational foundations. Without that hidden framework, galaxy formation would have been far slower and perhaps profoundly different. As the universe aged, clouds of hydrogen and helium gas drifted into these dark matter wells. Gas falling inward does not simply drop politely. It collides, compresses, heats, radiates energy, cools, and settles. Streams merge, turbulence develops, regions fragment, some material overshoots and swings around, some condenses further. Inside denser pockets of gas, gravity once again took charge on smaller scales. These pockets became the birthplaces of the first stars. Now, the first stars were not necessarily like the Sun. In fact, they were likely much more massive. The early universe contained almost no heavy elements. There was hydrogen, helium, and traces of lithium, but not the carbon, oxygen, iron, silicon, and other elements that later help gas cool efficiently. Because cooling was less effective, collapsing clouds often formed very large stars. Huge stars burn fast. A star many times the mass of the Sun lives a brief, intense life. It shines fiercely, pours radiation into surrounding space, and ends dramatically. Some explode as supernovae. Others may collapse directly into black holes. Either way, they do not linger. So the first stellar generation probably arrived like brilliant matches struck in a dark field, each one short-lived but transformative. Their light began rionizing the universe, stripping electrons from neutral hydrogen across intergalactic space. Their radiation heated nearby gas. Their explosions stirred surrounding material. Most importantly, inside their cores they forged heavier elements for the first time. Carbon, oxygen, magnesium, iron's early ancestors, the atoms in your blood, bones, breath and teeth, required stars to exist first. The first stars helped begin that chemical story. When these stars died, they scattered enriched material outward. Suddenly the universe had ingredients it did not possess before. Gas containing heavier elements cools more readily, fragments more easily, and can form smaller, more varied stars. That changed everything that followed. This is one reason galaxy formation is not merely about gathering matter. It is also about changing the rules as the process unfolds. The first stars altered their environments. Their winds pushed gas away from some regions while compressing others. Their explosions could halt local star formation temporarily, or trigger new waves elsewhere. Young proto-galaxies were not calm nurseries. They were busy, unstable places where creation and disruption happened together. Meanwhile, many small structures merged. Early galaxies did not usually appear as elegant, mature spirals. More often they were compact, irregular, clumpy systems colliding and combining. The modern universe contains grand galaxies with ordered disks and sweeping arms, but their ancestors often looked rougher, more chaotic and intensely active. Small dark matter halos merged into larger halos. Gas streams fed growing centers. Starbursts flared when fresh fuel arrived. Black holes may have formed early and begun accreting matter, adding energy and turbulence of their own. It was cosmic urban development with very little zoning law. And still, all of this took immense time by human standards. Millions of years for clouds to evolve. Tens or hundreds of millions for structures to grow. Billions for mature galaxies to emerge in familiar forms. We tend to imagine beginnings as moments, but many beginnings are eras. That includes our own Milky Way. The galaxy we inhabit did not spring into existence complete with spiral arms and a convenient location for Earth. It assembled gradually from smaller components. Ancient stars in the halo preserve clues of mergers long past. Streams of stars still arc through space. Remnants of smaller galaxies torn apart and absorbed. Even now, the Milky Way continues to evolve. Galaxies are less like finished monuments, and more like living cities that keep rebuilding themselves. There is something quietly comforting in that. We often think of the universe as fixed scenery, but it is not. Structures form, interact, age, and change. The sky above you may look steady over a single lifetime, yet on deeper timescales it is dynamic beyond measure. Even the serene spiral images we admire are snapshots in motion. If you could speed time forward, you would see galaxies feeding on gas, stars igniting, clusters shifting, companions merging, black holes flaring, arms reshaping, and stellar populations aging. You would see the patient consequences of gravity unfolding frame by frame. And if you sped time backward far enough, graceful galaxies would unravel into smaller fragments, then into gas clouds, then into faint density patterns in a young expanding universe, all complexity returning toward simplicity. Of course, simplicity can be deceptive. Those tiny early fluctuations contain the blueprint for everything to come, though blueprint is perhaps too intentional a word. No architect stood outside the cosmos drawing spiral plans. There were only laws, particles, expansion, chance differences, and enough time for consequences to accumulate. That may be one of the most astonishing truths in science. No hand arranged the stars one by one, yet order emerged. No one carved galactic disks, yet rotation organized them. No one planted heavy elements in advance, yet stars manufactured them. No one scheduled our arrival. Yet eventually, somewhere in one galaxy among trillions of stars, chemistry learned to ask questions about its own origins. And tonight, perhaps a little sleepily, here we are doing exactly that. Long before any galaxy turned slowly through the dark, before spiral arms curved like luminous pinwheels, before clusters of stars gathered into recognizable islands of light, the universe existed in a state so different from today that it can feel almost impossible to picture. There were no constellations, no glowing nebulae, no planets drifting around suns, no suns at all. If you had somehow arrived there as an observer, assuming the laws of survival were feeling unusually generous, you would not have looked up and seen a night sky. There was no night sky to speak of. There was only a young universe still becoming itself. When we speak of galaxies forming, it is tempting to imagine that space began empty and then later filled with stars the way houses appear in an undeveloped field. But the earliest cosmos was not empty land waiting for construction. It was full, dense, hot, active, and thoroughly uninterested in tidy arrangements. Structure had not yet emerged because conditions did not allow it. The ingredients existed in primitive form, but they had not yet learned how to gather. That is an important theme in cosmic history. The raw materials often arrive first, order comes later. To understand this era, we need to set aside the familiar picture of space as cold emptiness dotted with distant lights. The early universe was neither especially cold nor especially empty. It was expanding rapidly from an earlier hotter state, packed with energy and particles, changing moment by moment on timescales that would later seem unimaginably swift. If you could travel back far enough, matter as we know it would disappear into a more basic state. At extremely early times, temperatures were so high that atoms could not exist. Even atomic nuclei had not yet settled into stable combinations in the earliest instance. Conditions were too energetic for ordinary structures to hold together. Imagine trying to build a snowman in a furnace. Any form you create is immediately undone. That was the problem facing the young universe. Stability had to wait for cooling. As space expanded, temperatures dropped. This cooling was not caused by a cosmic air conditioner politely humming in the background. It happened because expansion spreads energy out. As the universe grew larger, the average energy density fell. That gradual lowering of temperature allowed new forms of matter to become possible in sequence. First came subatomic particles settling into more lasting roles. Then protons and neutrons combined into simple nuclei in a process known as primordial nucleosynthesis. This occurred within the first few minutes. Hydrogen nuclei formed abundantly. Helium nuclei formed in significant amounts. Tiny traces of lithium appeared, heavier elements, the sort later found in rocks, blood, oceans, and cookware, did not yet exist in meaningful quantities. So already the future universe had acquired some ingredients, but it still lacked one key convenience. Electrons were free. Because temperatures remained high, electrons could not remain attached to nuclei. If an electron tried to settle around a proton and make a neutral hydrogen atom, energetic photons would quickly knock it loose again. Matter therefore existed as plasma, a soup of charged particles mixed with radiation. This state behaves differently from ordinary gas. Charged particles respond strongly to electromagnetic forces, and light scatters constantly off free electrons. That means the early universe was opaque. You could not see across it in the usual sense because photons were trapped in an endless series of interactions. Every attempt by light to travel any distance ended in another collision. It was less like looking through clear air and more like trying to see through thick fog, if the fog itself were glowing and hotter than reason would recommend. This is one of the strangest facts about cosmic history. The universe had light before it had transparency. During this long plasma era, gravity was present, of course. Gravity does not take holidays. Yet large visible structures like galaxies could not simply assemble overnight. Matter and radiation were tightly coupled. Pressure resisted collapse. Space was expanding. The environment was energetic and restless. Conditions favoured smoothness more than clumping. And smoothness is exactly what we observe. When astronomers study the cosmic microwave background, the relic light released later when the fog cleared, they see evidence that the early universe was astonishingly uniform. Temperature differences from place to place were tiny, only slight variations on an otherwise even canvas. If the present universe resembles a landscape of mountains, valleys, oceans, forests, and cities, The earlier one was closer to a calm plane with barely noticeable ripples. That raises a useful question. If everything was so even, where did galaxies come from? The answer is hidden in those barely noticeable ripples. Perfect uniformity would be a problem for structure formation. If matter were distributed exactly equally everywhere, then every region would pull on every other region in balance. Nothing would gain an advantage. There would be no preferred place for collapse to begin. But the universe was not perfectly smooth. It was almost smooth. Almost is where galaxies live. Tiny fluctuations in density existed from very early times. Some regions had slightly more matter than average. Others had slightly less. The differences were minute, but gravity amplifies patience better than size. A denser region exerts a slightly stronger pull, drawing in nearby matter. As matter falls inward, the region becomes denser still, strengthening the pull further. Over immense time, a whisper of imbalance becomes a roar of structure. Yet before that long growth could fully unfold, another transformation had to occur. About 380,000 years after the Big Bang, the universe cooled enough for electrons to bind with nuclei and remain attached. Neutral atoms formed in large numbers, mostly hydrogen and helium. With far fewer free electrons to scatter from, photons could finally travel freely across space. The cosmic fog lifted. That released light still moves through the universe today, stretched by expansion into microwaves. It reaches our instruments as the cosmic microwave background, one of the most valuable sources of information in all astronomy. It is not merely old light. It is a record of the universe when structure was still in its infancy. At that moment, however, no galaxy yet shone. The universe had become transparent, but not luminous in the modern sense. There were no stars producing fresh starlight. After the glow of the background radiation faded with expansion, the cosmos entered a period sometimes called the Cosmic Dark Ages. This phrase sounds dramatic, but it is technically descriptive. Space contained neutral gas, mostly hydrogen and helium, but no stars had ignited yet. No galaxies glittered, no quasars blazed. The universe was full of matter, yet visually quiet. Picture a vast landscape before dawn, except the landscape is everywhere, and dawn will take millions of years. During this era, gravity continued its slow work. Regions with slightly more dark matter and ordinary matter drew in surroundings. Gas drifted toward denser zones. Small halos of dark matter formed and merged into larger ones. Ordinary matter, now able to move more freely without being so tightly tied to radiation, began falling into these gravitational wells. Still, from a human perspective, almost nothing seemed to happen. That is another recurring cosmic lesson. Enormous changes often proceed invisibly until thresholds are crossed. For millions of years, gas clouds accumulated mass. Temperatures shifted. Densities increased, turbulence developed. Cooling processes gradually allowed certain regions to compress further. Eventually, some pockets became dense enough that gravity overwhelmed internal pressure. Collapse accelerated. The first stars were preparing to ignite, but we are not there yet. For now, remain in the universe before galaxies, when all future splendor existed only as possibility. It is easy to underestimate such periods because they lack spectacle. We admire explosions, bright objects, dramatic collisions, and polished spiral galaxies. We are less impressed by diffuse hydrogen doing very little for a very long time. Yet without those quieter ages, nothing later appears. The same can be true in ordinary life. Growth often happens long before it looks visible. Now, let us consider how strange this early simplicity truly was. Today, matter is arranged into nested systems. Moons orbit planets. Planets orbit stars. Stars orbit galactic centers. Galaxies inhabit clusters. Clusters trace filaments of the cosmic web. The modern universe is hierarchical, structured across many scales. The early universe lacked nearly all of that hierarchy. There were no chemical ecosystems because heavy elements were absent. No rocky worlds because rock-forming atoms had not been forged in stars. No biology because the required chemistry did not exist. No long stellar histories because stars themselves had not formed. No black holes from stellar collapse. No supernova remnants. No dusty molecular clouds enriched by previous generations. In a sense, the universe was materially poor but physically rich. The laws governing everything were already present. Gravity, electromagnetism, nuclear forces, quantum processes, expansion dynamics, thermodynamics. The rulebook existed in full. The elaborate outcomes had simply not unfolded yet. That perspective can make the early cosmos feel less barren and more expectant. If you stood there somehow, you would not say, "Nothing is here." You might say, "Everything is waiting." Waiting for gas to gather, waiting for the first star to ignite, waiting for ultraviolet light to pour outward, waiting for the first heavy elements to be forged, waiting for the first proto-galaxies to emerge from halos, waiting for rotation, collision, feedback, chemistry, planets, oceans, cells, minds, memory, and questions. All of that lay ahead inside a universe that outwardly looked simple. There is also something humbling in the timescales involved. Human history spans a few thousand recorded years. Civilization, depending on how counted, covers only a sliver more. Yet the dark ages of the universe lasted tens to hundreds of millions of years before the first luminous structures transformed the scene. A person waiting for water to boil may feel deeply wronged after 3 minutes. The universe, by contrast, takes a broader view. Even so, these long intervals were not wasted time. Matter was moving. Gravity was sorting. Dark matter halos were assembling. Conditions were differentiating region by region. The seeds planted in primordial fluctuations were slowly germinating into future galaxies. And dark matter deserves a brief pause here, because before visible galaxies existed, invisible architecture was already taking shape. Since dark matter does not interact with light the way ordinary matter does, it could begin clustering efficiently earlier. It formed gravitational scaffolds that ordinary gas later followed. In many models of cosmic evolution, the unseen structure came first, and the luminous structure grew inside it. That means galaxies may be thought of not as isolated objects appearing in blank space, but as visible expressions of deeper hidden frameworks. There is something almost practical about that. The brightest things in the universe often depend on what cannot be seen directly. As the first dense regions deepened, ordinary gas fell inward and heated through compression. To continue collapsing, that gas needed ways to cool by radiating energy. Cooling allowed clouds to contract further, rather than simply remaining puffed up by pressure. Once enough cooling occurred in the right places, star formation could begin. And once stars begin, the universe changes quickly. But again, that belongs to the next stage. For now, stay with the darkness before dawn. No galaxies yet drifted across the black. No Milky Way stretched overhead. No Andromeda approached from afar. No telescopes existed naturally. But even if they had, there would have been little glitter to admire. Only subtle structure hidden in gas. Only gravity practicing patience. Only a universe between beginning and brilliance. There is a temptation to think that meaningful history begins when things become visible. Yet invisible eras often determine everything that follows. Foundations are not glamorous, but towers depend on them. Roots are not showy, but forests depend on them. The universe before galaxies was one immense foundation, and perhaps that is why astronomers study it so intensely. By examining the microwave background, by simulating dark matter collapse, by observing distant ancient galaxies whose light comes from near the cosmic dawn, scientists try to reconstruct the transition from simplicity to complexity. They ask how smooth matter became clumpy, how darkness became luminous, how gas became stars, and how stars became galaxies. In other words, they study how a quiet universe learned to make patterns. When we look at a mature galaxy, it can seem inevitable. There are stars arranged in sweeping disks, dense central bulges, orbiting clusters, clouds of gas, dust lanes, and perhaps a quietly hungry black hole at the centre managing its affairs with dramatic efficiency. The structure appears substantial, almost architectural. It is easy to imagine something so large must have begun with an equally large cause. Yet the first seeds of galaxies were not grand objects. They were tiny fluctuations, not mountains of matter, not giant clouds ready to collapse, not visible knots shining in space, just minute differences in density and temperature spread through the early universe. So small that if you could have measured them directly in that young era, you might have wondered why anyone was bothering. But those tiny irregularities became everything that followed. This is one of the most remarkable themes in cosmology. Enormous complexity can arise from very slight imbalance when enough time and gravity are available. To understand why these fluctuations mattered, we should return to the early universe after the hot, dense beginning, when matter and radiation filled space in a nearly uniform state. Nearly uniform is the important phrase. The cosmos was smooth to an astonishing degree. If you sampled one region and then another far away, the average conditions were very similar. Temperatures differed only by tiny fractions. Density varied only slightly, and yet not perfectly. Those imperfections were the opening move in the story of Galaxies. Imagine laying a fresh blanket across a bed. If it is pulled perfectly flat, marbles placed on it would not know where to roll. But if there are the faintest dips and rises, even barely visible ones, the marbles will begin to prefer certain directions. The tiniest contour becomes guidance. The young universe had contours of density. Some places contained a little more matter than average. Some contained a little less. Where matter was slightly denser, gravity pulled a bit more strongly. That extra pull attracted surrounding matter, increasing the density further. Regions with a deficit became relatively emptier as matter drifted away. Over vast spans of time, small differences grew into dramatic ones. Galaxies, clusters, and the large-scale cosmic web all trace back to those first uneven patches. Naturally, this invites another question. Where did the fluctuations come from in the first place? That takes us into the earliest known moments of cosmic history, to a period called inflation, or at least to the leading modern theory that includes it. Inflation proposes that the universe underwent an episode of extremely rapid expansion in a tiny fraction of a second after the Big Bang. Space itself expanded exponentially, stretching microscopic scales to enormous sizes. During that early era, quantum mechanics becomes deeply relevant. At very small scales, empty space is not truly empty in the ordinary sense. Quantum fields fluctuate, values jitter, tiny uncertainties are unavoidable. Normally such fluctuations remain microscopic and fleeting. But if inflation occurred, it could have taken these minuscule quantum irregularities and stretched them across cosmic distances. In simpler terms, the smallest random ripples may have been enlarged until they became the seeds of galaxies. That idea is extraordinary enough to deserve a pause. The stars above you, the Milky Way, clusters of galaxies, perhaps even the atoms in your body, may owe part of their existence to quantum fluctuations in the infant universe. Tiny randomness, expanded by cosmic growth, later sculpted by gravity. The universe appears to have an impressive talent for turning subtle noise into structure. Now we should be careful. Scientists continue refining models, testing observations and debating details. Cosmology is not a finished museum exhibit, but the broad picture is strongly supported by evidence. The pattern of fluctuations seen in the cosmic microwave background matches predictions from early universe physics with remarkable precision. That microwave background The afterglow released when the universe became transparent about 380,000 years after the Big Bang is one of our greatest windows into the era of fluctuations. When satellites such as COBE, WMAP, and later Planck mapped this radiation, they revealed slight temperature differences across the sky. These variations are tiny, roughly 1 part in 100,000, yet they correspond to the density ripples from which later structures grew. 1 part in 100,000 may sound laughably modest. It is the cosmological equivalent of being handed a single grain of flour and told to bake a continent. And yet gravity accepted the assignment. Suppose one region is just a little denser than its surroundings. Matter nearby feels slightly stronger attraction toward that region. As particles drift inward, the overdense patch gains mass. With more mass comes stronger gravity, which attracts still more matter. The process reinforces itself, not instantly, not dramatically at first, but steadily. Gravity is often described as weak compared with other forces, and in many contexts that is true. A small magnet can defeat the pull of an entire planet when lifting a paperclip. But gravity has 2 advantages that make it supreme on cosmic scales. First, it only attracts. It does not cancel itself through positive and negative charges the way electromagnetism can. Second, it works continuously over enormous distances and immense times. Given enough matter and enough patience, gravity becomes an empire builder. Meanwhile, the expanding universe complicates matters. Space itself was stretching, tending to separate regions from one another. So the growth of fluctuations was a contest between expansion pulling scales apart and gravity pulling matter together locally. Where density was too low, expansion dominated. Where density was high enough, collapse could eventually proceed. This balance determined where future galaxies would arise. Dark matter now enters the story in a major way. Ordinary matter in the early universe was tightly coupled to radiation before recombination, meaning it interacted strongly with light and pressure effects. This limited how quickly it could clump. Dark matter, however, did not couple to radiation in the same way. It could begin gathering earlier and more effectively. So while visible matter was still navigating a bright pressurized environment, dark matter was already constructing gravitational frameworks. Tiny fluctuations in dark matter density grew into halos, invisible concentrations of mass that later acted like wells into which gas could fall. If ordinary matter is the furniture, stars and lighting of a house, dark matter was the foundation poured before dawn. This is why galaxies did not emerge randomly scattered without pattern. They formed where the deeper gravitational landscape encouraged them. As fluctuations evolved, different scales behaved differently. Small overdensities could collapse earlier into compact halos. Larger regions took longer to gather, but ultimately produced galaxy groups, clusters, and superclusters. Matter did not simply clump into isolated blobs. It arranged itself into a network of nodes, filaments, sheets, and voids. Today, we call this the cosmic web. If you map millions of galaxies across large distances, you find they are not sprinkled evenly like sugar. They form strands and clusters separated by enormous emptier regions. This web-like arrangement is the mature descendant of those tiny primordial fluctuations. Again, the beginnings were subtle. No one standing in the early universe would have pointed dramatically and said, "There goes a filament." There were only slight statistical preferences, but statistics plus gravity plus time can become scenery. There is a comforting logic to this. Many meaningful things begin below the threshold of spectacle. A forest starts with seeds too small to shade anyone. A city starts with plans no tourist would photograph. A friendship may begin with one conversation. Galaxies began with fractions. Now let us talk about scale, because the mind naturally rebels here. When astronomers say tiny fluctuations, they do not necessarily mean tiny in size. The variations were small in amplitude, meaning the differences in density were slight. The regions themselves could span vast distances. Some ripples extended across scales that would later encompass many galaxies, so the early universe contained large areas that were only slightly denser or slightly thinner than average. Their contrast was weak, but their reach was immense. That distinction matters. A gentle slope across a continent is still a slope. Over time, as dark matter halos merged and ordinary gas followed, these seeded regions became the first proto-galactic sites. Gas collected, cooled, fragmented, and eventually formed stars. Some small halos may have hosted only brief bursts of star formation. Others merged repeatedly, becoming larger systems. Hierarchical growth, where smaller things combine into bigger ones, became a defining feature of cosmic structure. This means that the first seeds of everything were not blueprints for finished galaxies, in the way an acorn is a blueprint for a specific oak tree. They were more like starting conditions from which many outcomes could emerge depending on later interactions. Some regions experienced many mergers, some remained smaller, some fed central black holes efficiently, some were stripped by neighbours, some became giant ellipticals, some developed disks, some were disrupted entirely. The seeds mattered greatly, but history still mattered too. That is another subtle lesson in galaxy formation. Origins shape possibilities, yet later events shape identity. The same starting fluctuation could lead down very different paths depending on environment and timing. In crowded regions, mergers happened often. In quieter regions, isolated growth could allow graceful disks to survive. Nearby companions, gas supply, feedback from stars, and black hole activity all influenced what emerged. Still, none of that later variety erases the astonishing importance of the primordial ripples. Without them, no stars. Without stars, no heavy elements. Without heavy elements, no rocky planets. Without planets, no oceans of the familiar kind. Without chemistry rich enough to become biology, no listeners wondering about galaxies in the middle of the night. Sometimes the most consequential causes are nearly invisible at the start. Modern cosmology measures these fluctuations with exquisite care because they encode deep information about the universe. Their amplitude, distribution, and scale dependence tell scientists about inflation, dark matter, baryons, neutrinos, and the geometry of space. In a sense, the ripples are ancient fingerprints still pressed into the sky, and unlike many historical clues, they have not entirely vanished. The cosmic microwave background preserves them in youthful form. Large galaxy surveys preserve their grown-up descendants. Simulations run on supercomputers take the early ripples and evolve them forward under known physics, producing webs and galaxy populations strikingly similar to what telescopes observe. That agreement is one of science's quiet triumphs. It suggests that from a handful of equations, careful measurements, and a patient respect for evidence, humans have learned how to reconstruct events billions of years before Earth existed. Not bad for a species that still occasionally forgets where it left its keys. There is also beauty in the proportional mismatch here. The fluctuations were tiny, the consequences were colossal. We often expect big outcomes to require dramatic beginnings, but nature frequently disagrees. A slight imbalance in air can become a storm. A small genetic mutation can alter a lineage. A few degrees of temperature change can reshape climate. One additional fraction of density in the early cosmos can help determine where galaxies rise. The universe does not always shout its intentions. As time moved forward from those early ripples, gravity kept selecting winners and losers. Denser regions thickened. Underdense regions emptied further. Matter streamed along gradients. Halos formed, merged, and deepened. Gas accumulated. Cooling improved in local pockets. The stage for the first stars was being prepared. Soon, darkness would give way to ignition. Soon, the first luminous objects would begin changing their surroundings with radiation and explosions. Soon, proto-galaxies, rough and clumpy, would emerge from these once delicate contrasts. But before all brilliance, there were only fluctuations. Before all architecture, only contour. Before all islands of stars, only slight unevenness in a young expanding sea of matter and light. And if that feels surprising, perhaps it should. It reminds us that reality often hides great futures inside small beginnings. Once the first tiny fluctuations existed, the universe no longer faced a problem of complete sameness. It had something to work with. The differences were small, almost laughably so by everyday standards, but they were enough. From that point onward, one force began to matter more and more with each passing age. Gravity awakened. Not that gravity had ever been asleep, of course. It had been present from the beginning, woven into every interaction involving mass and energy. It shaped expansion, influenced motion, and quietly governed the broad behaviour of the cosmos from the earliest moments onward. But there is a difference between a force existing and a force becoming decisive. In the smooth young universe, gravity had little structure to amplify. Once fluctuations appeared, it gained footholds. Now it had places to pull toward. That shift changed everything. If you were somehow able to observe the early universe over millions of years compressed into a few seconds, you would not witness sudden fireworks. There would be no dramatic snap from emptiness into galaxies. Instead, you would see a slow migration, matter drifting, regions thickening, subtle streams developing as particles responded to the faintest gravitational advantages. The universe did not leap into structure. It leaned into it. This is important because galaxy formation is often misunderstood as a series of spectacular moments. While spectacular moments certainly arrive later, the foundation is built through patience. Gravity excels at patience. It does not need urgency. It does not tire. It simply keeps pulling. Imagine rainwater on a broad landscape after a storm. At first, the ground may look nearly flat, but tiny dips guide tiny flows. Water moves towards slightly lower places. Those places become wetter, which deepens channels, which attracts more flow, which deepens them further. After enough time, rivulets become streams, streams become rivers, and rivers reshape continents. Gravity did something similar with matter. Regions that were slightly denser than average exerted a slightly stronger pull. Nearby matter drifted inward. As it accumulated, the region became denser still, increasing the pull further. This positive feedback loop is one of the central engines of cosmic structure. Small preference became growing certainty, yet the process was not uncontested. The universe was still expanding. Space itself stretched between regions, trying in a sense to dilute matter and separate structures before they could fully collapse. So every forming concentration existed within a tension between outward expansion and inward attraction. Where density was too low, expansion won. Where density was high enough, gravity slowly took control. That threshold varied by scale and environment, but the principle remained. Galaxies formed where attraction eventually overcame dispersal. Now let us bring dark matter back into the room, because in this stage it becomes especially influential. Ordinary matter, the kind made of atoms, interacts through electromagnetism. Gas can heat, cool, collide, radiate, compress, and resist collapse through pressure. Dark matter appears to behave differently. It does not emit light or collide in the same ordinary way. It mainly participates gravitationally. This made dark matter extremely useful to gravity's long-term plans. Because dark matter did not experience pressure like hot gas, it could begin clustering efficiently into halos. These halos were concentrations of unseen mass, gravitational wells forming throughout the young cosmos. They did not glow. They did not announce themselves with fireworks, but they created landscapes ordinary matter would later follow. Think of invisible valleys forming before rivers arrive. As dark matter halos deepened, hydrogen and helium gas drifted toward them. Gas falling inward gains speed, and when gas streams meet or compress, they heat. Hot gas resists further collapse through pressure. So the journey from diffuse matter to stars and galaxies is not as simple as gravity pulls and everything falls together. There are negotiations. Gravity pulls inward, pressure pushes outward, cooling allows further contraction. Heating slows it down, motion creates orbits, collisions redistribute energy. The universe is not assembling furniture with an instruction manual. It is balancing competing physical effects until stable outcomes emerge. At first, many halos were small, tiny by cosmic standards, though still vast beyond human intuition. These miniature structures merged over time, joining into larger halos. This bottom-up growth, called hierarchical formation, is one reason galaxies have such rich histories. Large systems often began as collections of smaller ancestors. A future giant galaxy may once have been many little clumps sharing no common identity. There is something oddly familiar in that. Cities, languages, traditions, and even personal identities often form through accumulated mergers rather than single clean origins. As halos merged, their gravity stirred surrounding matter further. Gas did not fall neatly in straight lines. It arrived through filaments, streams, and chaotic flows. Some gas overshot centers and orbited, some shock-heated, some cooled rapidly, some were stripped during encounters, some remained diffuse for long periods. If you imagine early galaxy formation as elegant choreography, reality is closer to traffic merging in several dimensions with no lane markings. Still, patterns emerged. The densest central regions of halos became favoured sites for gas accumulation. As gas density increased, cooling processes became more effective in certain places. Cooling matters because hot gas puffs outward. To collapse into compact objects like stars, gas must lose energy. In the early universe, cooling channels were more limited than in later enriched eras, because heavy elements were scarce. Yet hydrogen-based processes and later molecular hydrogen could help under the right conditions. Once cooling gained enough ground, gravity could squeeze clouds further. That was the route toward the first stars. But before stars ignite, gravity does something else worth noticing. It creates time delays. We often imagine causes producing effects quickly. Strike a match, get flame. Drop a cup, hear regret almost instantly. But on cosmic scales, gravity's consequences can take millions or billions of years to mature. A fluctuation today, collapse much later. A merger now, transformed galaxy later. A halo forms, then waits for cooling, then waits for star formation, then reshapes through feedback. The universe is comfortable with deferred results. This can make the process feel slow to us, but slowness is not inactivity. During these ages, matter was constantly rearranging. Halos were growing. Filaments were feeding nodes. Density contrast sharpened. Hidden architecture thickened. If we could watch it sped up, it would look alive. Clouds would stream into wells. Small clumps would merge. Threads would connect hubs. Centers would pulse with fresh infall. Structures would continuously build and rebuild. Astronomers today simulate this using supercomputers. They start with the tiny fluctuations measured in the cosmic microwave background, apply known physics, and let virtual universes evolve. What emerges is extraordinary. Networks of filaments, halos, mergers, and eventually galaxies remarkably similar to the real cosmos. That success tells us something profound. Gravity plus realistic initial conditions can generate the large-scale universe we observe. No cosmic sculptor required. Now, let us consider why gravity becomes more dominant over time locally, even while the universe expands globally. As space grows, average matter density falls, but regions already denser than average can decouple from overall expansion. Their internal gravity binds them strongly enough that they stop following the general cosmic stretching in the same way. This is why galaxies do not expand internally as the universe expands. Bound systems resist that broad-scale growth. Your solar system is not stretching apart because of cosmic expansion. Neither is the Milky Way. Once gravity binds a structure sufficiently, local rules take over. That transition began first in the densest early regions. They ceased being mere participants in expansion and became self-gravitating systems with their own futures. One might say this is when matter begins choosing neighborhoods. Of course, gravity also creates motion rather than only collapse. Infalling material rarely arrives with zero sideways momentum. Tiny asymmetries in incoming flows generate angular momentum. As matter falls inward, conservation of angular momentum can spin systems up, just as an ice skater turns faster when drawing arms inward. This is one reason disks eventually form. Material that cannot fall straight into the center settles into rotating structures. Much later, these become the majestic galactic disks we admire, but their roots lie in these early imperfect infalls, where gravity gathers matter that never arrives perfectly head-on. Perfection is rare. Rotation is the consequence. There is another side to gravity's awakening: violence. When structures merge, gravitational energy converts into heat and motion. Gas shocks, orbits scramble, smaller systems can be torn apart, tidal forces stretch matter into streams, some mergers trigger intense bursts of star formation later by compressing gas dramatically. So gravity is not merely a gentle collector, it is also a disturber, mixer, and occasional demolitions expert. Yet even destructive events can contribute to growth. A smaller halo consumed by a larger one adds mass, momentum, gas, and stars. Debris from one structure becomes ingredients for another. The universe recycles disorder into new arrangements. There is comfort in that too. Not every collision is an ending. During these long ages before mature galaxies, no observer would have seen clean spiral arms yet. Many early systems were clumpy, irregular, compact, and turbulent. They were still under construction. Gravity was gathering materials faster than aesthetics could catch up. Modern galaxies are polished memoirs. Early galaxies were rough drafts. And what of us in all this? Every atom heavier than helium in your body required stars. Every star required gas collapse. Every gas collapse required gravitational gathering. Every gathering depended on fluctuations gravity could amplify. So in a very real sense, gravity's patient work in the young universe is part of your own ancestry. Bones, blood, breath, memory, and midnight curiosity all trace backward through stars to collapsing clouds, shaped by dark matter halos responding to ancient ripples. We are downstream of attraction. This may sound grand, but it is also practical. Without gravity doing the slow work, matter remains diffuse. No stars means no heavy elements, no planets, no chemistry complex enough for life as we know it. No listeners lying comfortably somewhere on Earth hearing about galaxies while trying not to stay too awake. Gravity built the stage on which later complexity could appear, and still, it was only beginning. As halos deepened and gas gathered, certain regions approached a crucial threshold. Density rose, cooling improved, pressure weakened relative to gravity. Clouds within clouds began collapsing further. Somewhere in that dark young cosmos, the first true stellar nurseries were taking shape. Soon, light would return in a new form. Soon, the first stars would ignite and begin transforming their surroundings with radiation, heat, and explosive endings. Soon, galaxy formation would become visible, but before brilliance there was pull. Before stars there was gathering. Before the heavens glittered, gravity spent ages quietly arranging the conditions that made glitter possible. By the time gravity had begun gathering matter into meaningful concentrations, the universe was no longer a smooth, nearly featureless expanse. Differences in density were growing. Regions were deepening into wells of attraction. Material was drifting, merging and settling into the first outlines of future structure. Yet if we could step back and watch that early cosmos unfold with perfect vision, we would notice something surprising. Much of the most important architecture was invisible. The galaxies we admire today are luminous things. They shine with billions of stars. They glow in infrared dust, radio gas, X-rays from hot plasma, ultraviolet bursts from young stellar nurseries, and sometimes with the fierce brilliance of matter spiraling into central black holes. Because of this, it is natural to think visible matter tells the main story. But in galaxy formation, visible matter often arrives after the stage has already been built. That hidden stage is dark matter. Now the phrase can sound mysterious, even theatrical, as though astronomers named it during a thunderstorm. In truth, the name is straightforward. It is called dark because it does not emit, absorb, or reflect light in ways we can easily detect. It is called matter because it appears to possess mass and therefore exerts gravity. We do not know its exact identity yet. That remains one of the major open questions in physics. But we know something substantial is there because the universe behaves as if it is. Galaxies rotate too quickly for their visible mass alone. Clusters of galaxies bend light more strongly than ordinary matter can explain. Large-scale cosmic structure forms in patterns best matched when dark matter is included. Again and again, gravity reports extra mass where telescopes do not see enough glowing stuff. It is one of science's strangest recurring messages. Something unseen keeps signing its name in gravitational ink. To understand why dark matter matters so much in the birth of galaxies, we should compare it with ordinary matter, the familiar kind made of atoms. Ordinary matter can collide, heat up, radiate energy, cool down, form molecules, ignite stars, and become listeners wrapped in blankets at inconvenient hours of the night. It is versatile, but it is also fussy. Gas pressure can resist collapse. Radiation can push it around. Heating can delay structure formation. Dark matter seems far less dramatic. It mostly responds to gravity and contributes gravity. It does not appear to collide much in the ordinary sense. It does not shine. It does not lose energy by radiating light the way gas can. It passes through the cosmic story like a silent contractor doing structural work before sunrise. That simplicity gave it a major advantage in the young universe. In the early eras, ordinary matter was strongly coupled to radiation. Hot photons scattered off charged particles, creating pressure that resisted clumping on smaller scales. Dark matter, not interacting with light in the same way, was free to begin gathering earlier. So while visible matter was still negotiating with heat and pressure, dark matter was already organizing itself into halos. These halos are crucial. A dark matter halo is a concentration of unseen mass bound together by gravity. They range enormously in size, from those associated with dwarf galaxies to immense halos surrounding galaxy clusters. In the early universe, smaller halos formed first, then merged into larger ones over time. Think of them as gravitational bowls appearing across space. Ordinary gas later flowed into those bowls. Without dark matter halos, ordinary matter would have had a much harder time assembling quickly enough into the galaxies we observe. The universe would likely look profoundly different. Structure formation would be slower, less efficient, and perhaps too delayed for the cosmic timeline we know. This is why dark matter is often described as the scaffolding of the universe. The metaphor is useful, though incomplete. Scaffolding usually gets removed after a building is finished. Dark matter does not leave. It remains around galaxies, enveloping them in vast halos extending far beyond visible stars. In fact, the luminous portion of a galaxy can be only a small central feature embedded inside a much larger dark halo. Imagine seeing a lamp in a field, and later discovering the lamp sits in the center of a stadium-sized invisible framework. That is closer to the truth than many realize. Let us consider the Milky Way, the galaxy you currently inhabit whether or not you filled out the residency forms. Our visible disk of stars, gas and dust spans roughly 100,000 light-years. Yet the Milky Way's dark matter halo extends much farther, reaching perhaps several 100,000 light-years or more. Neighbouring galaxies move within its gravitational influence. Satellite dwarf galaxies orbit inside it. We live not merely in a galaxy of stars, but in a galaxy nested within darkness. Now return with me to the time before the first stars. Tiny fluctuations in density from the early universe were growing. Regions slightly richer in dark matter attracted more dark matter. Halos formed and merged. Ordinary hydrogen and helium gas, influenced by these wells, began falling inward. As gas descended into a halo, it heated through compression and motion. Some of it could cool and sink further toward the centre. There, densities increased enough that stars eventually formed. This means the first visible galaxies likely emerged inside structures dark matter had already prepared. The invisible came first. There is something almost poetic about that, though we promise not to become too poetic. So let us instead call it practical. Foundations are often hidden. Dark matter also helps explain why galaxies rotate the way they do. If only visible matter were present, stars far from a galactic centre should orbit more slowly, much as planets farther from the Sun move more gently. Yet in many galaxies, outer stars move faster than expected. Rotation curves stay relatively flat. The missing gravity is supplied by dark matter. This discovery was one of the great clues that the luminous universe is not the whole inventory. Astronomers such as Vera Rubin and collaborators helped demonstrate these puzzling motions clearly, transforming the field. The stars were effectively telling us that something else was holding the system together. One should listen when billions of stars agree on a problem. Dark matter influences not only individual galaxies but their environments. Galaxies form along filaments of the cosmic web, where dark matter density is enhanced. These filaments intersect at nodes where clusters grow. Vast voids lie between denser strands. When astronomers map large galaxy surveys, the visible distribution traces an underlying dark framework. It is as though frost forms on the edges of a window pattern you cannot otherwise see. And because dark matter halos merge over time, galaxies inherit complex histories. A small halo may host an early dwarf galaxy. Later it falls into a larger halo, becoming a satellite. Tidal forces strip stars and dark matter into streams. Some satellites survive, others are absorbed. Large galaxies grow partly by consuming smaller companions. The Milky Way itself bears these marks. Stellar streams arch through its halo, remnants of smaller systems pulled apart over time. Even now, the Sagittarius dwarf spheroidal galaxy is being disrupted as it orbits us. Galaxy formation is not a single birth event. It is continuing inheritance, merger, and rearrangement inside dark matter structures. Naturally, a fair question arises. If dark matter is everywhere, why can't we just see it directly? Because seeing usually means detecting electromagnetic radiation, visible light, radio waves, X-rays, infrared, and so on. Dark matter does not appear to interact significantly through those channels. It neither shines like stars nor glows when heated in familiar ways. Instead, we infer it through gravitational effects. There are several methods. One is galaxy rotation, as mentioned. Another is gravitational lensing, predicted by Albert Einstein. Mass bends space-time, causing light from background galaxies to distort as it passes foreground mass. By measuring the distortion, astronomers can map where mass lies, including invisible mass. Clusters often reveal far more total mass through lensing than visible matter alone provides. There is also the cosmic microwave background, whose tiny fluctuations encode the composition of the early universe. Measurements indicate ordinary matter makes up only a modest fraction of total matter content. The rest appears dark. Then there are simulations. When scientists model a universe without dark matter, galaxies and large-scale structures fail to form in the observed way. Add dark matter, and the results become far more realistic. Sometimes the clearest evidence for something is how badly reality works without it. Still, we do not yet know what dark matter particles, if particles they are, truly consist of. Many candidates have been proposed: WIMPs, axions, sterile neutrinos, and others. Detectors deep underground listen for rare interactions. Particle accelerators search for hints. Astronomers keep refining constraints. So far, dark matter remains elusive. It is one of the rare situations where something can dominate the mass budget of galaxies while refusing to introduce itself properly. Despite this mystery, its role in galaxy formation is hard to overstate. Consider what happens when gas falls into a halo. The halo's gravity helps retain gas against energetic processes. Later, when the first stars explode as supernovae, they can blow gas outward. In small halos, such feedback may remove fuel and suppress future star formation. In larger halos, gravity can hold more gas, allowing richer growth. Thus, halo mass strongly influences what kind of galaxy develops. Tiny halos may host faint dwarf galaxies with few stars. Intermediate halos may build graceful spirals. Massive halos can support giant ellipticals, clusters, and hot gas atmospheres. Dark matter does not decide everything, but it sets the stage size and the available seating. There is also angular momentum. As halos grow through asymmetric inflows and mergers, they acquire spin. Gas falling into them can inherit this angular momentum and settle into rotating disks. Later, stars formed from that gas preserve the disk structure. So even the elegant spin of spiral galaxies may owe much to the growth histories of invisible halos. A beautiful visible disk can be the luminous expression of unseen dynamics. Now let us step back emotionally, if such a phrase may be allowed in cosmology. There is something humbling about learning that the glittering stars we notice are not the majority of matter-shaping galaxies. Human intuition naturally privileges what glows. We admire brightness, obvious motion, dramatic events. The universe seems less impressed by appearances. Much of what governs structure is dark, diffuse, and detectable only through careful reasoning. That pattern appears elsewhere too. Roots hold forests, foundations hold towers, microbes shape ecosystems. Hidden forces often outrank visible spectacle. After dark matter had begun assembling the hidden framework of the cosmos, the next major actor was ready to enter the stage more visibly. It did not arrive with drama. There were no fanfares, no instant galaxies, no sudden burst of neatly arranged stars. Instead, it came as something quiet, common, and deceptively simple. Hydrogen, the most abundant element in the universe. One proton, one electron, modest ambitions, extraordinary career. If the cosmos were a kitchen pantry, hydrogen would occupy nearly every shelf. It formed in great quantities during the earliest minutes after the Big Bang, and for long ages afterward it drifted through space with helium as the dominant ordinary matter available. Before planets, before oceans, before carbon chemistry, before starlight as we know it, there were immense clouds of hydrogen waiting for gravity to make introductions. This is where galaxy formation begins to feel less abstract. Tiny fluctuations and invisible halos are essential, but eventually matter must become tangible enough to gather into something denser, cooler, and more organized. The young universe contained vast reservoirs of gas. Mostly hydrogen atoms formed once the cosmic plasma cooled enough for electrons to remain bound to nuclei. When the universe became transparent and entered its long dark ages, these hydrogen atoms filled space in diffuse form. Not packed into bright nebulae yet, not compressed into stars, just spread widely across expanding space, responding to gravity's patient pull. Imagine mist stretched across a continent. Now imagine valleys slowly forming beneath it. That gives a rough sense of what happened as hydrogen gas encountered the gravitational wells created by dark matter halos. The gas began drifting inward, not all at once, not in straight lines, and not with any concern for our desire for tidy diagrams. It moved through filaments, streams, eddies, and uneven flows. The universe was learning how to inhale. Where dark matter halos were stronger, more gas collected. As hydrogen fell inward, gravitational energy converted into heat. This is a crucial point. Falling matter speeds up, and when gas compresses or collides, temperature rises. So gravity alone does not instantly create stars. It often creates hot gas first. Hot gas resists further collapse through pressure. This means the road from diffuse hydrogen to the first stars required another ingredient. Cooling. Gas must lose energy if it is to condense into smaller, denser structures. Without cooling, clouds remain puffed up and reluctant to contract. In later cosmic eras, heavy elements and dust help cooling significantly. But in the early universe, those substances barely existed. No previous stars had yet forged carbon, oxygen, silicon, iron, or other useful coolants in meaningful amounts. The first hydrogen clouds had to work with simpler tools. One of those tools was molecular hydrogen, known as H2. Under certain conditions, hydrogen atoms could combine into molecules. These molecules are especially important because they can radiate energy efficiently through rotational and vibrational transitions, allowing gas to cool further. That may sound technical, but its consequence is straightforward. Molecular hydrogen helped the first cloud shrink. Without it, early star formation would have been much harder. So within dark matter halos, ordinary hydrogen gas gathered, heated, partially cooled, and continued contracting. Some regions became denser than others. Turbulence stirred the clouds. Streams collided. Shock fronts formed. Matter fragmented into clumps. Inside those clumps, gravity intensified again. This pattern repeats throughout cosmic history. Large structures gather into smaller structures, which gather into smaller ones still, until stars are born. The earliest hydrogen clouds were immense beyond everyday intuition. Even a modest proto-galactic gas reservoir could contain masses millions of times greater than the Sun. Yet these giant clouds were extremely diffuse compared with air on Earth. Space offers a useful lesson in scale. Something can be vast and thin at the same time. A cloud hundreds of light years across may contain fewer particles per cubic centimetre than the best-stocked vacuum. Still, given enough volume, the totals become staggering. Now, because the early universe lacked metals, these first clouds likely behaved differently from modern star-forming nebulae. Cooling was less efficient, fragmentation may have been coarser, and the masses of resulting stars were often larger. Rather than producing many small sun-like stars immediately, some early clouds may have favoured the formation of massive stars tens or even hundreds of times the Sun's mass. Those stars would burn hot, live briefly, and die spectacularly. But we are not at ignition yet. For now, remain in the cloud stage, because clouds are where possibility concentrates. Hydrogen in the early universe was not arranged randomly forever. The cosmic web guided it. Gas streamed along filaments toward denser nodes where halos resided. These filaments acted like highways of supply, feeding growing systems continuously. Even today, simulations suggest galaxies gain gas not only through mergers, but through long, cold streams flowing inward from intergalactic space. So galaxy formation was never simply one cloud collapses. It was supply chains, inflows, replenishment, and environment. A young halo sitting at the intersection of filaments might receive rich streams of fresh gas. Another in a quieter region might grow more slowly. Cosmic location mattered. It still does. There is something surprisingly urban about this. Some cities thrive because roads, rivers, and trade routes meet there. Some galaxies grew because matter streams converged there. As hydrogen accumulated, rotation also entered the picture. Infalling gas rarely arrives perfectly head-on. Tinier symmetries create angular momentum. As clouds contract, spin increases. This can flatten material into rotating structures, early ancestors of later disks. Even before spiral galaxies unfurled graceful arms, their raw ingredients were already learning to turn. Hydrogen clouds also interacted with radiation backgrounds. As the first stars began appearing elsewhere, ultraviolet light could heat nearby gas or break apart molecular hydrogen, making cooling harder in some regions while encouraging collapse in others through compression fronts. The young universe quickly became a place where one forming object influenced another. Creation was contagious, but so was disruption. This interplay means the first breaths of galaxy formation were uneven. Some halos formed stars early. Some were delayed. Some lost gas through feedback. Some continued gathering quietly until thresholds were reached later. There was no single dawn switch flipped everywhere at once. Instead, light spread patch by patch through a universe still mostly dark. Let us pause on the symbolism of hydrogen for a moment, though only gently. Nearly every water molecule you have ever drunk contains hydrogen atoms whose lineage traces ultimately to the earliest universe. The hydrogen in your body is ancient in a way heavier elements are not. Oxygen in water had to be forged in stars later. Hydrogen arrived near the beginning, so when we speak of primordial hydrogen clouds becoming the first galaxies, we're also speaking of matter still present in you now. Some atoms are excellent travellers. Back in those early clouds, collapse became increasingly localized. A giant gas reservoir might contain many denser knots. Each knot could continue shrinking if cooling remained effective. As densities rose, gravitational collapse accelerated. Temperatures climbed in central cores. Eventually protostars would emerge. The first stars likely formed in relative isolation or small groups, compared with modern giant star clusters. Their radiation then transformed surrounding gas dramatically. Powerful ultraviolet light ionized hydrogen nearby, heating and dispersing some material while leaving other regions compressed. A single, massive early star could act like a lighthouse and a leaf blower simultaneously. This feedback is essential to understanding why galaxy formation is self-regulating rather than purely runaway. Gravity pulls gas inward, but stars formed from that gas can heat and expel it. The result is a balance of inflow and resistance. Even in infancy, galaxies were negotiating with themselves. There is also the matter of timescale. Human intuition struggles here because clouds in our experience change quickly. Weather shifts in hours. Smoke disperses in minutes. Steam vanishes from tea with regrettable speed. Cosmic hydrogen clouds evolve over millions of years. Their motions are majestic mainly because they are slow. If sped up, however, they would appear alive. Filaments would funnel gas inward. Clouds would swell and fragment. Dense knots would brighten. Shock waves would ripple. Fresh streams would replenish emptied zones. It would look less like static space and more like weather on the largest scale imaginable. Modern telescopes can glimpse some of these processes indirectly by observing very distant galaxies whose light comes from the early universe. Instruments such as NASA's James Webb Space Telescope are helping reveal galaxies already forming surprisingly early, rich with gas and active starbirth. Each observation refines our understanding of how quickly clouds condensed and how efficiently stars ignited. The story continues to sharpen, yet even with better images, the principle remains elegantly simple. No stars without gas, no gas gathering without gravity, no early galaxy without hydrogen clouds learning to collapse. And because hydrogen was everywhere, the possibility of galaxies was everywhere conditions allowed. Some clouds would become dwarf systems, some would merge into larger protogalaxies. Some would feed central black holes, some would be disrupted by neighbours, some would form stars, lose gas, then recover later. The cloud stage did not determine one destiny. It created many futures. That is worth remembering. Beginnings often provide options rather than final forms. For a very long stretch of cosmic history, the universe had matter, motion, gravity, expanding space, and enormous potential, yet it lacked something we instinctively associate with a living cosmos: fresh light. There had been light before, of course. The early universe was once a hot, radiant plasma glowing intensely. Later, when atoms formed and space became transparent, relic radiation streamed freely in every direction. We still detect that ancient afterglow today as the cosmic microwave background, but as expansion continued, that radiation stretched and cooled. It dimmed into microwaves, no longer the brilliant illumination of a youthful universe. Then came the Dark Ages. Not darkness in the dramatic sense of pure nothingness, but darkness in the practical astronomical sense. There were no stars yet, no galaxies full of shining suns, no quasars blazing across vast distances. Space was filled mostly with hydrogen and helium gas drifting through invisible dark matter structures, waiting for gravity to complete its patient preparations. The universe had fuel, it had frameworks, it had clouds collapsing in deepening wells. Now it was ready for ignition. Somewhere inside dense pockets of primordial gas, the first stars began to form. This moment was one of the great turning points in cosmic history. It is difficult to overstate its importance. Before stars, the universe was chemically simple. After stars, complexity begins. Before stars, light was leftover radiation from beginnings. After stars, new sources of energy switched on across the dark. The cosmos started making its own lamps. To understand how the first stars formed, picture those vast hydrogen clouds we discussed earlier. Gravity pulled gas inward, raising density. Cooling processes, especially involving molecular hydrogen, allowed some regions to lose energy and contract further. Within those regions, smaller clumps formed. As a clump collapsed, its center became hotter and denser. Eventually, the core reached extraordinary temperatures and pressures. When conditions became extreme enough, hydrogen nuclei began fusing into helium. Nuclear fusion had started. A star was born. Fusion is the engine of starlight. In a star's core, matter is converted into energy according to the famous relation described by Albert Einstein. A tiny amount of mass becomes a tremendous amount of energy. That energy fights gravity's inward squeeze, creating balance. A stable star is essentially a long negotiation between collapse and explosion, gravity pulling in, pressure pushing out. The first stars entered that negotiation under unusual circumstances. Modern stars form in environments enriched by earlier generations. Gas today contains heavier elements such as carbon, oxygen, silicon, iron, and dust grains that help cooling and fragmentation. But the first stars formed from almost pristine material, mostly hydrogen and helium, with virtually no metals in the astronomical sense. Astronomers call these earlier stars Population 3 stars. The name sounds like a well-organized committee, but it simply refers to a classification scheme. Population 1 stars, like the Sun, are metal-rich and younger. Population 2 stars are older and metal-poor. Population 3 stars are the hypothetical first generation, formed before stellar enrichment. Because primordial gas cooled less efficiently than enriched gas, many models suggest these first stars were unusually massive. Rather than forming mostly modest stars like our Sun, early clouds may have produced giants tens, perhaps hundreds of solar masses. Massive stars live fast. They burn hotter, they shine brighter, they die younger. So the first stars may have been dazzling but brief. Cosmic mayflies with extraordinary power. Imagine the first one switching on in a dark region of the universe. For millions of years there had been only diffuse gas and faint background radiation. Then suddenly a new point of fierce ultraviolet light appears, pouring energy into surrounding space. That must have been quite a neighborhood change. The star's radiation ionized nearby hydrogen, stripping electrons from atoms and creating expanding bubbles of hot ionized gas. These ionized regions grew outward, overlapping with others as more stars formed elsewhere. Over time, this process helped reionize much of the universe, ending the cosmic dark ages. This period is known as the Epoch of Reionization. It marks the transformation of intergalactic hydrogen from mostly neutral gas back into ionized plasma due to the first luminous sources. The exact timeline is still being refined through observations, but it likely unfolded over hundreds of millions of years as stars and early galaxies multiplied. The darkness did not vanish all at once. It retreated in patches. One region lit first, another later. Bubbles of ionization expanded, collided, merged, and spread. The universe became a place of advancing dawns. That phrase may sound poetic, but it is also physically accurate enough to keep. The first stars did more than provide light. They also changed temperature conditions in their surroundings. Ultraviolet radiation heated nearby gas, which could prevent fresh collapse in some regions by increasing pressure. In other places, shock fronts and compressed shells triggered new star formation. So the first stars were both creators and interrupters. That pattern continues throughout galaxy history. Stars are not passive decorations. They shape the ecosystems that make them. Now let us consider just how bright these early giants may have been. A star dozens of times more massive than the Sun can outshine it enormously. Surface temperatures rise. Ultraviolet output becomes intense. Lifetimes shrink to only a few million years, short compared with the Sun's expected 10 billion year main sequence career. If the Sun is a patient candle, some first stars were industrial floodlights with no retirement plan. And because they lived briefly, the first stars quickly led to the next great transformation. They died. Massive stars often end as supernovae, violent explosions that eject enriched material into space. Some extremely massive ones may have undergone pair instability supernovae, destroying themselves completely. Others likely collapsed into black holes, perhaps seeding the first generations of larger black holes that later grew into supermassive monsters at galactic centers. So from the first stars came heavy elements, turbulence, shock waves, black holes, and more light-producing descendants. One ignition opened many doors. The chemistry of the universe changed profoundly. Before stars, there was almost no carbon for organic molecules, no oxygen for water beyond future combinations, no silicon for rocks, no iron for planetary cores, no calcium for bones, no phosphorus for DNA-like chemistry. Stellar fusion began forging these ingredients, though many would require later generations and explosive endings to disperse fully. In a literal sense, stars manufacture possibility. This is why the phrase, "we are made of star stuff," often associated with Carl Sagan, is not merely sentimental. It is chemically accurate. But before any later stars enriched galaxies broadly, the first stars had to begin the process. They were the opening factory shift. There is another reason the first stars matter deeply for galaxy formation. Their radiation and explosions influenced how gas behaved inside early halos. Small halos might lose gas if stellar feedback was strong enough, slowing future star formation. Larger halos could retain more material and continue growing. This helped determine which early systems became robust galaxies and which remained faint or intermittent. So the first stars were not just passengers inside proto-galaxies, they were engineers of galactic futures. Observationally, these first stars are difficult to detect directly. Individual population 3 stars likely lived too briefly and too far back in time for easy observation with present instruments. But astronomers search for indirect evidence through chemical signatures in ancient metal-poor stars, distant galaxy spectra, and theoretical models. Some stars in our own Milky Way halo preserve clues. Extremely metal-poor stars may have formed from gas enriched by only one or a few early supernovae. Their compositions are like archaeological fragments from a vanished era. The oldest surviving stars can function as fossils of stars that did not survive. Modern observatories such as James Webb Space Telescope are also pushing the frontier by identifying galaxies from surprisingly early cosmic times. These young galaxies likely hosted intense star formation, and perhaps stars with properties closer to primordial populations than later stars possess. Each distant detection is a message delayed by billions of years. Now let us pause and imagine the emotional scale of this transition, while keeping both feet planted in science. For hundreds of millions of years, no starry sky existed anywhere. Then gradually points of light began appearing across space, not all at once, not visible to any waiting audience, but one by one, regions that had known only diffuse gas gained brilliant centers. The universe became punctuated. Dark expanses gained landmarks. Energy found local homes. It is tempting to think of light as merely illumination, but in astrophysics, light is information. It reveals temperature, composition, motion, density, magnetic fields, and distance. When the first stars ignited, the universe became easier to read, even if no readers yet existed. There is a practical lesson in that too. Creation often involves becoming visible after long invisible preparation. Gas collapsed unseen for ages. Then ignition made the process obvious. Many transformations in nature work this way. The public notices the bloom, not the roots. As more first stars formed, clustered, died, and were replaced, small proto-galaxies brightened. Their combined radiation accelerated ionization. Their heavy elements improved cooling for later gas clouds. Their remnants seeded future complexity. What began as isolated stellar fires became a network effect. Soon, galaxies would no longer be hypothetical destinations of gravity. They would be luminous, active systems with populations of stars, chemical evolution, internal feedback, and growing structures. Rough, chaotic, compact perhaps, but unmistakably real. The sky of the universe had changed permanently. And we are downstream of that change. Every sunrise on Earth depends on stellar fusion. Every atom of oxygen you breathe required generations of stars. Every telescope image of a spiral galaxy traces back through earlier populations to these first pioneers. The first stars did not know they were making future planets possible. They did not know they were enriching gas for life, or creating black hole seeds, or ending darkness on large scales. They simply obeyed physics intensely. The first stars did not arrive quietly, but compared with what came next, their births were only the beginning of the spectacle. Once those massive primordial stars ignited, the universe gained new light, new heat, and new chemistry. Yet their greatest influence often came at the end of their short lives. They exploded, and with those explosions nearly every later chapter of galaxy formation changed course. When we think of fireworks, we usually imagine something decorative, brief, and perhaps accompanied by someone insisting you look at this one. Cosmic fireworks are less polite. Stellar explosions can outshine entire galaxies for a time, hurl matter across space at enormous speeds, generate shock waves larger than solar systems, and forge elements essential to planets and life. The earliest universe needed this violence. Without it, galaxies would remain chemically primitive, star formation would proceed differently, and the path toward complex worlds would be far narrower. So let us return to those first stars, the likely population 3 giants born from pristine hydrogen and helium clouds. Many were probably far more massive than the Sun. Massive stars consume fuel rapidly because their cores run at extreme temperatures and pressures. Gravity squeezes harder, fusion burns faster, and lifetimes shrink dramatically. A star many times the Sun's mass may live only a few million years. That sounds long until compared with the Sun's expected 10 billion year career. By stellar standards, some early stars were all sprint and no pension. During life, these stars already changed their surroundings through ultraviolet radiation and powerful stellar winds. Their light ionized nearby hydrogen, heating gas and altering future collapse. Their winds pushed material outward, stirred turbulence, and carved cavities into surrounding clouds. Then came death. For many massive stars, the final act is a supernova, where nuclear fusion in the core can no longer support the star against gravity. Collapse begins rapidly. Outer layers crash inward, rebound through complex processes, and the star tears itself apart in an explosion of astonishing energy. For the earliest very massive stars, some may have undergone pair instability supernovae, a special kind of explosion in which the entire star can be disrupted, leaving no remnant behind. Others likely collapsed into black holes after explosive or partially explosive endings. Either way, calm was not the dominant mood. Now consider what a supernova does to a young protogalaxy. Until then, much of the gas is mostly hydrogen and helium. Heavy elements are scarce. Cooling pathways are limited. Future generations of stars have fewer ingredients to work with. A supernova changes that in one violent moment. Inside stars, fusion builds heavier nuclei step by step. Carbon, oxygen, neon, magnesium, silicon, sulfur, and eventually iron group elements emerge in layered interiors depending on stellar mass and stage. During explosive death, even more elements can be synthesized and then expelled outward. The debris races into surrounding space. For the first time, the interstellar medium becomes enriched. This is one of the most consequential upgrades in cosmic history. Before stellar enrichment, gas clouds were simple. After enrichment, gas clouds had new cooling agents, new chemistry, and the seeds of future planets. The carbon in living molecules, the oxygen in water, the silicon in rocks, the iron in blood and planetary cores, the calcium in bones, the phosphorus in DNA-like systems, all depend on stars and often on stars dying dramatically enough to distribute their work. The early universe was not given these ingredients at the start. It had to earn them through explosions. There is something almost practical about this. The universe does not waste previous generations, it recycles them. When a supernova blast wave expands, it does more than scatter atoms. It compresses nearby gas. Shock fronts can trigger fresh star formation by squeezing clouds into collapse. In other regions, the same explosion may disperse gas and temporarily suppress star formation. So stellar death can both create and delay future birth. That balance is a recurring theme in galaxies. Too little feedback, and gas collapses too quickly. Too much feedback, and gas is blown away. Somewhere in between, galaxies regulate themselves. The first protogalaxies were especially sensitive because many were small. Their gravitational wells, though significant, were shallower than those of large modern galaxies. A powerful supernova in a low-mass halo could expel substantial gas, starving future star formation for a time. In a larger halo, more gas might be retained, allowing continued growth. This means early explosions helped sort the winners and strugglers of galaxy evolution. A dwarf system might flare briefly with stars, then lose fuel. A larger system might absorb the shock, keep gas, and continue building. Thus, fireworks influence demographics. There is another consequence often overlooked: turbulence. Galactic gas is not supposed to behave like a neat, still pond. It churns, mixes, shears, and swirls. Supernovae inject kinetic energy into that medium, stirring it continuously. Metals produced in one region spread into others. Temperatures become patchy. Density structures form and dissolve. The earliest galaxies likely looked less like elegant spirals and more like compact storm systems, full of bright clusters, disturbed gas, and repeated blasts. Modern galaxy images can mislead us into imagining smooth order from the beginning. Reality usually starts rough. Now let us think bigger than one star. As many first stars formed across many halos, their combined radiation and explosions transformed the wider universe. Ionized bubbles around star-forming regions expanded and merged. Reionization progressed. Heavy elements leaked from galaxies into intergalactic space through winds and outflows. Black hole remnants may have begun accreting gas, adding X-rays and further heating. Local events became cosmic trends. What started as separate stellar lives became environmental change on the scale of the universe. Astronomers search for evidence of this enrichment in several ways. Very distant galaxies observed with James Webb's Space Telescope already show signs of surprisingly rapid chemical evolution. Ancient stars in the Milky Way halo preserve unusual elemental ratios that may reflect one or a few early supernova ancestors. Intergalactic gas seen in absorption spectra contains metals that must have been ejected long ago. Even now, the universe carries fingerprints of its earliest explosions. One might ask why massive early stars were so influential compared with smaller stars. The answer is partly brightness and partly lifespan. Massive stars emit tremendous ultraviolet radiation, affecting large regions quickly. Then they die fast, returning processed material soon after formation. Smaller stars, by contrast, can live for billions or trillions of years depending on mass, contributing more slowly. The early universe benefited from urgency. It needed fast chemists, and that is what giant stars provided. There is also the matter of black holes. Some first stars may have collapsed directly into black holes tens or hundreds of times the Sun's mass. In dense early environments, mergers and accretion could grow these seeds further. Over time, some may have contributed to the formation of the supermassive black holes found in galactic centers. So when early stars died, some became engines for future quasars. Again, endings became beginnings. This recycling logic appears everywhere in astrophysics. Old stars seed new clouds. Supernova remnants compress fresh nurseries. Dead cores become neutron stars or black holes. Mergers build larger systems from smaller ones. Galaxies themselves grow partly by absorbing companions. The cosmos is remarkably unwilling to throw anything useful away. Now, let us bring this down to a personal scale, because cosmic chemistry eventually becomes intimate chemistry. The iron in your blood was forged in stars and often dispersed through stellar explosions. The oxygen you breathe required generations of fusion and ejection. Calcium in your teeth, iodine in biology, trace metals in your cells, all descend from processes like these. Your body is partly archived supernova debris with opinions. That sentence is scientifically respectable enough to keep. But before life, before planets, before even long-lived sun-like stars became common, those first explosions had to enrich their neighborhoods. Once gas contains metals, cooling becomes more efficient. Dust grains can form, clouds fragment more readily, lower mass stars become easier to produce. This was another turning point. The first stars were likely unusual giants. Their descendants could become more diverse. With each generation, galaxies gained complexity. Star clusters formed, mixed stellar populations emerged, gas dynamics changed. Planet formation became increasingly possible around later stars. The path towards systems like our own Sun gradually opened. All because early stars were generous in death. Of course, generous from the viewpoint of nearby gas may be debatable. If you are a hydrogen cloud minding your own collapse and a supernova shockwave arrives at thousands of kilometers per second, you may file a complaint. But on longer timescales, disturbance often creates opportunity. There is a broader lesson hidden there. Stability can preserve, but disruption can transform. The early universe needed both. As cosmic fireworks continued, small proto-galaxies merged into larger ones. Their enriched gas mixed. New starbursts flared when collisions compressed clouds. Some systems lost gas to winds, others retained enough to flourish. Diversity of galaxy types began to emerge from shared rough beginnings. No two growth histories were identical. Environment mattered, timing mattered, mass mattered, feedback mattered, history mattered. Yet all of them were now operating in a changed universe, one no longer made only of primordial simplicity. The first stars had rewritten the chemical rules. After the first stars lit the darkness and their explosive endings enriched surrounding gas, the universe entered a new phase. It was no longer a place of mostly smooth hydrogen waiting for the first spark. It had light sources, it had feedback, it had turbulence, radiation, metals, black hole remnants, and growing concentrations of matter shaped by dark matter halos. Most importantly, it had momentum. The cosmos was beginning to organize itself into systems that would one day be recognized as galaxies. Not mature galaxies yet. Not elegant spirals with symmetrical arms, or giant ellipticals with calm rounded glow. Those would come later. What emerged first were rougher, smaller, busier ancestors, proto-galaxies. The word simply means early forming galaxies, but it deserves more respect than sounding like a temporary model number. These were the first durable star systems where gas, stars, dark matter and gravity began operating together as long-term communities rather than isolated incidents. That distinction matters. A single first star in a dark halo is important. A recurring environment that forms many stars, retains some gas, exchanges material, merges with neighbours, and develops internal structure is something new entirely. It is the difference between a campfire and a town. To picture the first proto-galaxies, set aside the polished photographs of modern galaxies that often decorate textbooks. Early systems were typically compact, irregular, clumpy, and highly active. They did not yet have billions of years of settling behind them. They were under construction while occupied. Imagine a city where roads are still being poured, buildings are rising, deliveries arrive constantly, and fireworks go off at random intervals. That is closer to the truth than the serene spiral postcard version. These proto-galaxies formed inside dark matter halos that had grown through earlier collapse and mergers. Gas flowed inward along filaments of the cosmic web, feeding dense centers. Some gas cooled and collapsed into stars. Some was heated by stellar radiation or shocks. Some was blown outward by supernovae, only to fall back later or escape entirely. Nothing was static. This constant cycling of gas is one reason galaxies are better understood as processes than objects. A proto-galaxy was not merely a container full of stars. It was an ecosystem of inflow, outflow, collapse, enrichment, and renewal. Fresh gas entered, stars formed, stars changed the gas. Gas moved again. The cycle repeated. Now, let us consider size. Many first proto-galaxies were modest compared with later giants. Some may have contained only millions of stars, perhaps fewer. Others grew rapidly through mergers and steady inflow. In cosmic terms, they were seedlings. Yet even a small proto-galaxy could span enormous distances by human standards and contain masses beyond comprehension. Scale in astronomy remains determined to embarrass intuition. Because these early systems were smaller and denser, star formation could be intense. Gas fractions were high. Material had not yet been exhausted by billions of years of stellar history. Streams of cold gas from surrounding filaments often continued feeding central regions. This could trigger starbursts, episodes of rapid star formation where many stars formed over relatively short timescales. A young proto-galaxy might spend long periods turbulent and active, converting gas into stars at rates that would exhaust its supply quickly if not replenished. Fortunately for it, the cosmic web often supplied refills. Even galaxies appreciate dependable logistics. The internal appearance of these systems likely varied dramatically. Some may have shown several bright star-forming knots rather than one smooth structure. Others could be elongated, disturbed by recent mergers, or surrounded by streams of infalling gas. Ordered disks may have existed in some cases, but many early galaxies were dynamically hot, meaning stars and gas moved in more chaotic ways than in calm, settled disks. Order takes time. That sentence applies widely. Modern spiral galaxies like the Milky Way owe much of their graceful appearance to long-term settling, rotation, and continued evolution. Early proto-galaxies had not enjoyed those luxuries yet. They were younger, rougher, and more frequently interrupted by collisions. Collisions are central to this story. In the early universe, matter was packed into a smaller overall cosmic volume than today, and structures were still assembling rapidly. Halos merged often. When two protogalaxies encountered one another, gravity distorted their shapes, stirred gas, and sometimes combined them into a larger system. Stars usually pass one another safely because space inside galaxies is vast, but gas clouds collide, compress, and shock. This can trigger fresh star formation. So mergers are not merely destructive, they're creative chaos. Two messy systems can become one bigger messy system with fireworks. Repeated mergers built mass hierarchically. Small structures combined into medium ones. Medium ones contributed to larger future galaxies. This bottom-up growth is one reason galaxies contain layered histories. Ancient stars may come from absorbed dwarfs. Stellar streams can mark former companions. Bulges may reflect old mergers. Halos preserve archaeological clues. Galaxies are partly built from memory. Now let us discuss metals, meaning elements heavier than helium in astronomical language. Thanks to earlier stellar generations, protogalactic gas was no longer pristine. It contained traces of carbon, oxygen, silicon, iron, and more. These elements improved cooling efficiency. Gas could radiate energy more effectively, fragment into smaller clouds, and form a wider range of stars. This changed the stellar population. Instead of mainly giant primordial stars, later generations increasingly included lower-mass stars, some of which could survive for billions of years. A few ancient low-mass stars from very early times may still exist today, quiet witnesses to a turbulent youth. That possibility is remarkable. Some stars currently orbiting in old galactic halos may have formed when the universe was only a small fraction of its current age. They are less stars than time capsules. Protogalaxies also likely hosted growing black holes in some centers. Black hole seeds from early massive star remnants or direct collapse scenarios could accrete gas. As matter spiraled inward, enormous energy was released. In some cases, this may have created active galactic nuclei or early quasars. So while stars were lighting neighborhoods, black holes were beginning executive management. These central engines could heat gas, drive outflows, and regulate star formation, adding another feedback loop to already complicated systems. The first protogalaxies therefore contained many competing influences: gravity pulling gas inward, rotation redistributing motion, supernovae stirring and ejecting gas, radiation heating clouds, mergers scrambling structure, black holes adding energetic disruption, fresh inflows replenishing fuel. And somehow, through all of this, galaxies emerged. There is a lesson here about complexity. Stable systems do not always arise from calm beginnings. Sometimes they arise because competing forces keep shaping one another until durable patterns form. Astronomers today observe very distant galaxies whose light has travelled more than 13 billion years. Many appear compact, bright, clumpy, and actively star-forming. Instruments such as the James Webb Space Telescope are revealing that substantial galaxies existed earlier than once expected. Each distant image is not just a picture, it is a delayed report from protogalactic times. Some early systems already show significant mass and surprising maturity. Others remain irregular and intensely active. This variety suggests galaxy assembly was neither uniform nor synchronized. Some regions advanced quickly, others developed more gradually. Cosmic history is broad enough to allow many schedules. There is also environment. Protogalaxies and dense regions where many halos clustered likely merged often and grew fast, becoming ancestors of future giant galaxies and clusters. Those in quieter areas may have evolved more gently, preserving smaller forms longer. Location influenced destiny. The same is true in cities, forests, economies, and apparently universes. Now let us narrow the lens to a single hypothetical protogalaxy. It sits in a dark matter halo drawing gas from nearby filaments. Several bright star-forming clumps blaze near its centre. Massive young stars flood nearby clouds with ultraviolet light. Supernovae from slightly older stars carve hot bubbles through gas. A small companion galaxy approaches, already stretched by tidal forces. Streams of enriched material arc outward. At the centre, perhaps a black hole accretes modestly. New gas continues arriving from outside. This is not a finished galaxy. This is a galaxy learning to be one. And over millions of years, repeated cycles smooth some chaos into structure. Rotation becomes more coherent. Stars disperse into broader distributions. Mergers in large mass. Gas settles into thicker disks or central reservoirs. Feedback regulates extremes. Slowly, the temporary becomes persistent. That transition is one of the great achievements of gravity and time working together. There is something comforting in that. The first stable forms of many things are messy. Perfection is usually a late luxury. For us, protogalaxies matter because they are our ancestry at a grand scale. The Milky Way almost certainly passed through phases like these. It did not begin as a calm spiral suitable for desktop wallpapers. It grew through mergers, bursts of star formation, halo assembly, and long-term settling. Ancient stars in our halo, globular clusters and stellar streams still preserve traces of that history. We live inside a polished descendant of former chaos. Once the first protogalaxies had formed, the universe did not politely leave them alone. There was no moment when gravity stepped back, dusted off its hands, and declared the job complete. If anything, galaxy formation was only entering a more social phase. Galaxies grow by meeting. That sentence sounds warmer than the reality sometimes deserves. These meetings were not tea visits. They were close encounters between vast systems of stars, gas, dust, dark matter, and black holes, each carrying its own momentum and history. Some passed by and continued on. Some exchanged material. Some tore streams from one another. Some merged completely into larger descendants. Again and again, across billions of years, interactions shaped the visible universe. This is one of the most important ideas in modern astronomy. Galaxies are not isolated ornaments hanging separately in space. They belong to neighborhoods, groups, clusters, and filaments. Gravity connects them. Motion brings them together. Their histories are entangled. If you could watch the cosmos in accelerated time, galaxies would not appear fixed and serene. They would drift, approach, distort, collide, combine, and continue moving in an endless choreography of consequences. The elegant still images we admire are snapshots taken mid-dance. To understand why mergers matter so much, recall that early galaxies formed hierarchically. Small dark matter halos collapsed first. These hosted small protogalaxies. Over time, halos merged into larger halos, bringing their galaxies with them. As the invisible frameworks combined, the luminous structures inside also interacted. Small systems fed larger systems. This bottom-up assembly remains a cornerstone of galaxy formation theory. A giant galaxy seen today may be the cumulative result of hundreds or thousands of smaller mergers, accretions, and absorbed companions spread across cosmic time. It does not necessarily begin giant. It became giant through repeated encounters. That process is humblingly incremental. Suppose two galaxies approach one another. Human instinct expects stars to crash together like billiard balls. In truth, stars inside galaxies are so widely separated that direct star-star collisions are rare during galactic mergers. Space within galaxies is mostly space. So what happens instead? Gravity happens. As the galaxies draw near, tidal forces distort their shapes. Long streams of stars and gas can be pulled outward into tails and bridges. Orbits of stars become scrambled. dark matter halos overlap and merge. Most dramatically, gas clouds within the galaxies can collide, compress, and lose energy. Gas, unlike stars, is collisional and messy. When gas is compressed during a merger, it can trigger intense star formation known as a starburst. Regions that once formed stars modestly may suddenly ignite thousands or millions of new stars over relatively short periods. The galaxies brighten, massive young stars appear, supernova rates later increase. In short, collisions can make galaxies briefly exuberant. This is why some interacting galaxies in the modern universe glow with extraordinary activity. They are not merely damaged, they are productive chaos. A famous nearby example is antennae galaxies, two colliding galaxies with spectacular tidal tails and vigorous star formation. They provide a glimpse of processes common throughout cosmic history. In the early universe, such encounters were even more frequent. Structures were closer together on average, smaller systems were abundant, and assembly was rapid. Young galaxies lived in crowded developmental environments. Growth by merger was not occasional background noise, it was a central mechanism. Now, not every encounter ends in full union. Some galaxies pass one another on trajectories too fast or too distant for immediate merging. Yet even flybys can matter. A close passage may trigger bars, spiral patterns, bursts of star formation, or tidal stripping. A small satellite can lose stars and gas to a larger neighbour over repeated orbits, gradually dissolving into streams. This is happening in our own neighbourhood. The Sagittarius dwarf spheroidal galaxy is being torn apart by the Milky Way, leaving stellar streams wrapped around our galaxy. Galactic hospitality can be complicated. There are broadly two kinds of mergers astronomers often discuss: major and minor. A major merger occurs when two galaxies of roughly comparable size combine. These events can dramatically reshape both participants. Ordered disks may be disrupted. Stars are thrown onto new random orbits. Gas funnels inward. Central black holes may later merge. The resulting galaxy can become more spheroidal or elliptical in character. A minor merger involves a large galaxy consuming a much smaller companion. These are gentler in some respects, but extremely common. Over time, repeated minor mergers can add substantial mass, thicken disks, grow halos, and supply fresh gas or stars. Think of major mergers as corporate takeovers between equals, and minor mergers as a steady stream of acquisitions no one outside finance enjoys hearing about. Both build galaxies. Now let us consider the Milky Way again, because it offers a familiar address in an unfamiliar story. Our galaxy likely grew through many mergers over billions of years. Evidence survives in stellar streams, halo stars with distinct chemical signatures, and ancient globular clusters. One notable past event, often called the Gaia Sausage Enceladus merger, appears to have involved a significant early collision that helped shape the Milky Way's inner halo. Even galaxies with calm current appearances may have rowdy youth behind them, and our future remains social. The Andromeda Galaxy is approaching the Milky Way. In roughly 4 to 5 billion years, the two galaxies are expected to interact and eventually merge. Do not cancel tomorrow's plans. This is not imminent by human scheduling standards. When that future merger unfolds, many stars will simply pass by one another. Gas clouds may collide, new star formation may flare, the central black holes may eventually coalesce. A larger remnant galaxy, sometimes nicknamed Milky Way, in cheerful defiance of naming dignity, will emerge. So galaxy growth by meeting is not ancient history alone. It is ongoing policy. Mergers also influence supermassive black holes. Many galaxies host central black holes, and when galaxies merge, those black holes can sink toward the new center through dynamical friction, eventually forming binaries and perhaps merging themselves. Such events produce gravitational waves, ripples in space-time predicted by Albert Einstein, and now observed from stellar mass mergers by detectors like LIGO Scientific Collaboration. Future observatories aim to detect the lower frequency waves from giant black hole mergers. Thus, galactic encounters reshape not only stars and gas, but space-time itself. Another major effect of mergers is morphological diversity, meaning galaxy shape. Why are some galaxies spirals, others ellipticals, others irregular? Part of the answer lies in merger history. A galaxy that experiences a quiet life with steady gas accretion and limited major disruption may preserve a rotating disk and develop spiral structure. One subjected to repeated major mergers may lose ordered rotation, leaving stars on more random orbits and producing an elliptical form. History becomes geometry. That is a satisfying phrase because it is broadly true. Environment matters here too. Dense galaxy clusters contain many interactions, though very high relative speeds can reduce full mergers while increasing harassment and stripping. Smaller groups, where velocities are lower, may be especially fertile grounds for mergers. Where you live affects how often neighbours rearrange your furniture. Gas supply also determines whether mergers build or extinguish future growth. If interacting galaxies contain abundant cold gas, starbursts can occur. If they are gas poor, the merger may mostly redistribute existing stars and dark matter, producing less dramatic new star formation. So the same broad event, a merger, can lead to very different visible outcomes depending on timing and ingredients. Astronomers observe this across cosmic time. Deep surveys show that mergers were more common in the earlier universe. Many distant galaxies appear clumpy, disturbed, or interacting. This fits the expectation that young cosmic epochs were active assembly periods. Modern giants often carry the scars of those eras. Sometimes scars are subtle. Outer halos of stars may preserve shells, streams, and ripples from long ago accreted companions. These features can be faint and require sensitive imaging, but they reveal that even seemingly settled galaxies are layered with absorbed histories. A galaxy can look calm while remembering everything. There is also a deeper philosophical comfort in mergers. Growth in the universe is rarely solitary. Systems become larger, richer, and more complex through contact, exchange, disruption, and incorporation. Material from one galaxy becomes part of another. Stars born in a dwarf system may end up orbiting a giant host billions of years later. Origins are not always final addresses. Even the atoms around us may have travelled through multiple galactic environments before joining the cloud that formed the Sun and its planets. Now imagine a young proto-galaxy in the early universe. It has recently formed stars, its gas is turbulent, and fresh streams feed it from nearby filaments. A smaller companion approaches. Tidal forces stretch both systems. Gas compresses. New stars ignite in blue clusters. Dark matter halos overlap. Over time, the pair coalesces into one large galaxy with more mass, altered spin, richer chemistry, and a changed future. Repeat this millions of times across the universe. That is how cosmic cities grow. Far out in the universe, some of the largest structures ever assembled do something surprisingly graceful. They turn. Not all galaxies spin in the same way, and not every galaxy is dominated by orderly rotation, but many of the most recognizable ones, especially spiral galaxies, are vast rotating systems of stars, gas, dust, and dark matter. Their disks circle around central regions in motions that continue for billions of years. Our own Milky Way is one of them. The Sun, carrying Earth and the rest of the solar system along with it, orbits the galactic centre at tremendous speed, while we go about ordinary concerns like emails, groceries, and occasionally forgetting why we entered a room. That raises an excellent question. Why do galaxies spin at all? After everything we have explored so far, dark matter halos, collapsing gas clouds, proto-galaxies, mergers, starbursts, and cosmic growth by repeated encounters, rotation might seem like a natural bonus feature. But it is not automatic. If matter simply fell inward perfectly symmetrically from every direction, much of it would collapse straight toward the centre. There would be little net spin. The resulting structures would look very different. Yet the universe is not built from perfect symmetry. That turns out to be fortunate for anyone who appreciates spiral galaxies. The origin of galactic rotation begins with something called angular momentum. This is the physical quantity associated with rotational motion. It is conserved, meaning it cannot simply vanish or appear from nowhere in an isolated system. If a cloud of matter has even a tiny amount of sideways motion as it collapses, that rotational tendency becomes increasingly important as the cloud contracts. You have seen a version of this in everyday life. A spinning figure skater turns faster when pulling arms inward. The rotational motion becomes more obvious as the size shrinks. In astronomy, collapsing gas clouds and forming halos follow similar principles, though usually without sequins. The young universe supplied many opportunities for tiny asymmetries. Matter did not fall into dark matter halos in perfectly straight balanced flows. Nearby structures tugged gravitationally. Filaments fed halos from preferred directions. Neighbouring halos passed by. Mergers occurred at angles. Streams of gas arrived unevenly. All of these influences generated torque. Torque is the twisting effect of a force applied off-centre. If one side of a forming halo is pulled more strongly than another, a spin can develop or be enhanced. This process, known in cosmology as tidal torque theory, helps explain how early halos acquired angular momentum through interactions with surrounding structures. So galaxies did not begin spinning because someone wound them up. They were twisted into motion by the uneven gravitational environment of the early universe. That is an elegant idea. Rotation emerges not from perfect isolation, but from relationship. Consider a forming dark matter halo surrounded by other lumps of matter. Their gravity pulls on it from different directions. Because the mass distribution is irregular, these pulls do not cancel neatly. The protohalo experiences a net twisting influence over time. As it grows and collapses, that angular momentum becomes embedded in the system. Later, gas falling into the halo inherits much of this rotational tendency. Gas behaves differently from dark matter because gas can collide and lose energy. As it falls inward, it heats, cools, and settles. Material moving with angular momentum cannot simply plunge directly into the centre unless it sheds that momentum somehow. Instead, much of it spreads into a rotating disk. This is one of the most important steps in creating spiral galaxies. The gas flattens because collisions between particles dissipate vertical random motion more efficiently than organised rotation around the centre. Over time, the material becomes thinner and more disk-like. New stars forming from that gas inherit the disk's motion. A galaxy disk is therefore not just matter orbiting randomly. It is matter that has settled into a preferred rotational arrangement. That arrangement can persist for immense spans of time. Now let us pause to appreciate scale. The Sun orbits the centre of the Milky Way at roughly 220 kilometers per second, give or take depending on the model used. That is about 790,000 kilometers per hour. Even at that speed, one full orbit takes around 225 to 250 million years. Dinosaurs appeared and vanished during less than 2 galactic years. So while galaxies spin, they do so on schedules that make impatience look deeply impractical. Rotation also helps galaxies resist total collapse. Gravity constantly tries to pull matter inward. Orbital motion provides a balancing effect. Stars in a disk are not falling straight into the centre because they are moving sideways fast enough to remain in orbit, much as Earth orbits the Sun rather than plunging into it. This means galactic structure is partly a negotiated truce between inward pull and sideways motion. Without sufficient angular momentum, a galaxy might become much more compact and spheroidal. With strong rotational support, disks can flourish. That helps explain why some galaxies are spirals and others are ellipticals. Spiral galaxies are often strongly influenced by ordered rotation. Their stars in the disk move on roughly circular orbits around the centre. Elliptical galaxies, by contrast, are more dominated by random stellar motions. Stars move in many directions rather than sharing one coherent disk rotation. Such systems often result from major mergers that scramble previous ordered disks. History determines motion. A galaxy that grows relatively gently with steady gas inflow and limited catastrophic disruption has a better chance of preserving or rebuilding a rotating disk. A galaxy repeatedly battered by large mergers may lose that elegant organisation. So when you see a spiral galaxy, you are partly seeing a calmer biography. When you see an elliptical, you may be seeing the aftermath of rougher times. Naturally, even spiral galaxies are not simple rigid wheels. Different parts rotate at different speeds. Inner regions orbit faster in angular rate than outer regions, meaning the galaxy does not spin like a solid dinner plate. If it did, spiral arms would remain fixed in place neatly forever. Instead, galaxies experience differential rotation. This has fascinating consequences. If spiral arms were made of the same fixed stars always staying together, differential rotation would wind them tightly over time until they disappeared into an absurd cosmic cinnamon roll. Yet many spirals persist. The leading explanation is that spiral arms are often density waves or recurring patterns, rather than permanent material structures. Stars and gas move in and out of the arms. The arms are regions of enhanced density, where gas compression can trigger star formation, making them bright and visible. In other words, a spiral arm may be more like a traffic jam than a painted stripe. Cars move through the jam, but the pattern remains. That is one of astronomy's most satisfying analogies because it makes a majestic cosmic feature sound oddly relatable. Rotation also feeds central structures. Gas in disks can gradually lose angular momentum through bars, instabilities, or interactions, allowing it to drift inward. This can nourish star formation near galactic centers or feed central black holes. So even while angular momentum supports disks broadly, redistributing it locally can drive intense activity. Galaxies are constantly moving momentum around like accountants managing a very large and complicated budget. Dark matter remains essential here as well. The visible disk rotates within a much larger dark matter halo. The halo contributes significantly to the gravitational field, especially in outer regions. This helps explain why rotation speeds of stars far from the centre stay higher than visible matter alone would predict. The spin we observe is therefore a luminous performance happening inside an invisible framework. Astronomers measure galactic rotation using spectroscopy. Light from stars and gas is shifted by motion through the Doppler effect. Material moving toward us is slightly blue shifted. Material moving away is red shifted. By mapping these shifts across a galaxy, scientists reconstruct rotational patterns. It is one of the great achievements of modern science that humans can infer the turning of systems millions of light years away by examining tiny changes in light. Meanwhile, early galaxies in the distant universe often appear messier. Some already show signs of rotating disks surprisingly soon after the Big Bang. Others remain turbulent and clumpy. Observations from the James Webb Space Telescope and other instruments are helping reveal how quickly organised rotation emerged. The answer appears to be earlier than many expected, though not universally. Some young galaxies seem to settle into disks fast. Others take longer. The universe enjoys variety more than standardization. There is also something philosophically pleasant about rotation. Straight collapse is simple but terminal. Orbit allows duration. Because matter moves around centers rather than directly into them, structures can persist. Stars circle for billions of years. Gas clouds survive long enough to form new stars. Planets remain in stable environments. Sideways motion creates time. Without orbital balance, many cosmic systems would be brief or impossible. That includes us. The solar system exists because a rotating disk around the young sun conserved angular momentum. Earth orbits because motion balances gravity. The Sun orbits the Milky Way because galactic gravity and velocity are in long-term conversation. We live inside nested rotations, spin within orbit within spin within orbit. And yet these motions feel still because we move with them. No one on Earth senses the planet's path around the Sun directly in daily life. Few of us feel the Sun's galactic journey while making tea. Motion at steady speed can feel like rest. The universe is full of movement disguised as stability. As galaxies matured, rotation helped shape their identities. Some developed bars crossing their centers, some built grand spiral arms, some retained gas-rich disks where stars continued forming. Others lost gas, faded or transformed through mergers into more chaotic systems. But the turning began much earlier, in those first asymmetrical collapses and tidal talks of the young cosmos. A slight twist became a disk became a galaxy became a home for stars, planets, and eventually curious minds asking why anything spins at all. Look through a catalogue of galaxies and one thing becomes immediately clear. The universe does not mass-produce a single design. Some galaxies spread wide, elegant spiral arms around bright central bulges. Others appear smooth and rounded, with little obvious internal pattern. Some look chaotic, lopsided, torn, or patchy, as though they were interrupted halfway through deciding what to become. There are giants larger than imagination, dwarfs barely noticeable beside them, systems rich with gas and youthful stars, and others old, quiet, and largely finished with dramatic activity. This diversity is not cosmetic. A galaxy's shape tells a story. It reveals clues about motion, gas supply, star formation, merger history, environment, and time. Morphology, the scientific term for form or structure, is one of astronomy's most useful windows into how galaxies live and evolve. So when we ask why galaxies look different, we're really asking why their histories diverged. The broad classical categories most people encounter are spiral, elliptical, and irregular. Reality is more nuanced, of course. Astronomers enjoy subclasses, edge cases, lenticular galaxies, bars, rings, dwarfs, tidal remnants, and enough labels to reassure any librarian. But these three major families provide an excellent map. Let us begin with the most photogenic citizens, spiral galaxies. A spiral galaxy usually consists of a flattened rotating disk containing stars, gas, and dust, plus a central bulge and surrounding halo. Curving arms wind outward through the disk. These arms are often bright because gas is compressed there, triggering new star formation. Massive young blue stars illuminate the pattern, making spirals especially striking. Our own Milky Way belongs to this family, likely a barred spiral with a central bar-shaped structure feeding material inward and helping organize motion in the disk. Spiral galaxies are dynamic systems supported strongly by rotation. Their stars in the disk move in relatively orderly orbits around the center. Gas remains abundant in many spirals, allowing continued star formation over long periods. Dust lanes thread through arms. New stars are born in giant molecular clouds. Supernovae enrich future generations. Spirals are often places where the story is still actively being written. They are not always calm, but they are frequently productive. Why does a galaxy become spiral rather than something else? Usually because it retained or regained a rotating disk of gas. If a galaxy experiences steady gas accretion, moderate interactions, and avoids too many catastrophic major mergers, a disk can survive or reform. Angular momentum remains organized. Star formation continues within that rotating structure. In short, spirals often reflect a history where rotation stayed meaningful. Now let's move to a very different temperament: elliptical galaxies. These systems range from nearly spherical to elongated oval forms. They generally lack prominent spiral arms and often contain much less cold gas than spirals. Star formation is low or absent in many of them. Their stellar populations are frequently older and redder, meaning many bright young blue stars are no longer being created in abundance. Instead of stars orbiting in a thin disk with shared orderly rotation, stars in ellipticals often move on many different paths. Random motions dominate more than clean rotational support. If spirals are like organized traffic circles, ellipticals are more like vast swarms whose motions average into a smooth shape. How do such galaxies form? One major pathway is merging. When two spiral galaxies of comparable size undergo a major merger, gravitational interactions can scramble their ordered disks. Stars are thrown onto new orbits in many directions. Gas may trigger a final starburst, then later be exhausted, heated, or expelled. The remnant can settle into a smoother elliptical galaxy. Repeated mergers over time strengthen this trend. Thus, many ellipticals are products of rough social histories. The largest ellipticals often live in dense galaxy clusters, where mergers and interactions have been common across billions of years. Some giant ellipticals may have grown by cannibalizing numerous smaller companions. Their smooth appearance can hide a very chaotic past. A polished exterior is not always evidence of a peaceful life. There is another common category, one less tidy but no less important: irregular galaxies. These are systems lacking obvious spiral or elliptical symmetry. They may appear patchy, asymmetric, distorted, or clumpy. Some are intrinsically small dwarf galaxies whose modest gravity never organized a grand disk. Others are galaxies disrupted by nearby neighbors, tidal forces, or recent collisions. Irregular does not mean uninteresting, quite the opposite. Many irregular galaxies are rich in gas and vigorous star formation. Their turbulence and bright star-forming regions make them valuable laboratories for understanding galaxy growth under less settled conditions. A famous nearby example is the Large Magellanic Cloud, an irregular satellite of the Milky Way. It hosts active star-forming regions such as the Tarantula Nebula, one of the most energetic nearby stellar nurseries. Its shape may owe much to interactions with both the small Magellanic Cloud and the Milky Way itself. Which brings us to a crucial point. Shapes are not fixed identities. Galaxies can transform. A spiral galaxy can merge and become elliptical. An irregular galaxy can settle into a disk if conditions allow. A gas-poor spiral may fade and lose distinct arms. Interactions can trigger bars, rings, tidal tails, warps, and temporary distortions. Morphology is not merely inherited at birth. It evolves. This makes galaxies feel less like species and more like weather patterns with long memories. Time is one of the strongest sculptors of shape. In the early universe, many galaxies looked clumpier and more chaotic than many nearby mature systems. Observations from the James Webb Space Telescope and earlier deep surveys reveal compact, turbulent, irregular structures at great distances, meaning we see them as they were billions of years ago. That fits expectation. Young galaxies were assembling rapidly, fed by fresh gas, disturbed by frequent mergers, and still learning internal order. The graceful spirals common in the nearby universe often required long stretches of relative stability to emerge fully. Beauty can be a late-stage phenomenon. Environment matters greatly too. Galaxies in crowded clusters often experience stripping by hot intra-cluster gas, repeated flybys, tidal harassment, and mergers. These processes can remove gas, suppress star formation, and encourage smoother forms like ellipticals or lenticulars. Galaxies in quieter regions may preserve gas-rich disks longer and continue forming stars. Where you live affects what shape you become. That sentence applies beyond astronomy, but we shall keep our focus responsibly cosmic. Now let us talk briefly about bars, because many spiral galaxies possess them. A bar is an elongated structure of stars crossing the central region. Bars can channel gas inward, feeding central star formation or black hole activity. They also redistribute angular momentum within the disk. The Milky Way likely has one, so our home galaxy is not simply a spiral. It is a barred spiral with internal engineering underway. There are also ring galaxies, often formed by collisions where one galaxy passes through another, sending density waves outward like ripples in a pond. There are lenticular galaxies, disc-shaped but lacking strong spiral arms, and often gas-poor, perhaps transitional systems between spirals and ellipticals. Nature enjoys gradients more than boxes. Astronomers historically use systems such as the Hubble tuning fork diagram, developed by Edwin Hubble, to classify galaxies by appearance. Though useful, modern understanding emphasizes that these categories are not a simple evolutionary ladder. A galaxy does not necessarily march neatly from one branch to another. History is more tangled than diagrams. The stars within different shapes also tell stories. Spirals often contain younger blue stars in arms, and older populations in bulges. Ellipticals tend to host older, redder stars overall. Irregulars may show patchy bursts of young stars amid mixed populations. So colour, shape, gas content and motion all work together as clues. Astronomers combine imaging, spectroscopy, simulations and surveys to decode these clues. By measuring stellar motions, gas distribution, chemical composition and environment, they reconstruct how a galaxy likely arrived at its current form. A galaxy is not just seen, it is interpreted. There is something deeply satisfying in that. The night sky offers patterns, and science teaches us to read them. On a personal scale, this variety means the universe is not repetitive scenery. It is creative through rules. The same physical laws, gravity, angular momentum, thermodynamics, dark matter, and time generate wildly different outcomes depending on starting conditions and later encounters. Give the cosmos hydrogen, gravity, and enough patience, and it refuses to make only one shape. That may be one reason galaxy images feel so compelling. They combine order and individuality. Each one follows physics, none are copies. Even our own galaxy likely wore different faces in the past. It was smaller once, rougher once, merger shaken once, less enriched once. Billions of years from now, when the Andromeda Galaxy merges with the Milky Way, both spirals may lose their current identities and become something more elliptical. The sky's familiar forms are temporary, yet temporary on timescales generous enough to be comforting. Hidden inside many galaxies, including some of the grandest structures in the universe, there is often something both compact and enormous, quiet and influential, invisible and impossible to ignore once you know it is there, a black hole. More specifically, in many galactic centers there lives a supermassive black hole, an object containing millions, sometimes billions, of times the mass of the Sun packed into a region small compared with the galaxy surrounding it. These central black holes do not usually swallow entire galaxies like enthusiastic vacuum cleaners, despite their public reputation. They are not cosmic monsters roaming through star systems at random. Most of the time they sit near galactic centers and exert influence through gravity, energy release, and long-term feedback. That influence can be profound. This is why astronomers increasingly view them not as strange side features, but as important participants in galaxy evolution. Hence our phrase tonight, silent architects. The word silent is appropriate because black holes emit no light from within the event horizon itself. The architect part is earned because the environment around them can shape the growth of whole galaxies. To understand how, let us begin with scale. A galaxy may contain hundreds of billions of stars spread across tens or hundreds of thousands of light years. Its central black hole, by contrast, occupies a tiny region. If size alone determined importance, it would seem negligible. But gravity does not vote by volume. Mass concentrated at the center matters. More importantly, matter falling toward a black hole can release extraordinary energy before crossing the horizon. Gas spiraling inward forms an accretion disk, where friction and compression heat material to immense temperatures. This hot disk can radiate across the electromagnetic spectrum, From radio to X-rays, when feeding actively, a central black hole can outshine the stars of its host galaxy. That is how quasars and active galactic nuclei are born. A quasar is the brilliant beacon of a rapidly accreting supermassive black hole. Seen from billions of light years away, some quasars are among the brightest persistent objects in the universe. Yet the light does not come from the black hole itself. It comes from matter in distress nearby. This distinction is worth keeping. Black holes are dark. Their dining rooms are not. Now consider the early universe. We have already followed the formation of first stars, proto-galaxies, mergers and growing structures. Somewhere amid that turbulence, black hole seeds likely emerged. There are several leading possibilities. One route begins with massive early stars. When such stars die, some may collapse into black holes tens or hundreds of solar masses. Over time, mergers and gas accretion could grow these seeds larger. Another possibility is direct collapse. Under certain conditions, a huge gas cloud in a young halo might avoid fragmenting into stars and instead collapse more directly into a massive black hole seed. There are also hybrid scenarios involving dense star clusters and runaway mergers. The exact pathways remain active areas of research, but observations show that supermassive black holes existed surprisingly early. Distant quasars seen less than 1 billion years after the Big Bang already host black holes with enormous masses. This has caused many astronomers to raise one eyebrow professionally. Growing such giants so quickly is challenging, which means the early universe was efficient, unusual, or both. As galaxies formed, black holes and their hosts appear to have evolved together. A remarkable clue is the correlation between central black hole mass and properties of the galactic bulge, especially stellar velocity dispersion. In simplified terms, bigger bulges often host bigger black holes. That relationship suggests connection. How can an object tiny compared with the whole galaxy know anything about the stars far beyond it? The answer likely involves feedback. Feedback in astronomy means outputs from a process altering future inputs. A central black hole that accretes gas can produce radiation, winds, and jets. These outputs heat or expel surrounding gas. If enough gas is removed or prevented from cooling, star formation across larger regions can slow dramatically. So while a galaxy feeds the black hole with gas, the black hole may respond by limiting how much gas remains available for future stars. That is an impressively complicated roommate arrangement. There are two broad modes often discussed. In radiative or quasar mode, high accretion rates generate intense radiation and winds. This is common in luminous active galaxies, especially earlier cosmic epochs when gas was plentiful. In jet or radio mode, lower accretion rates can still launch powerful jets of relativistic particles. These jets can inflate bubbles in hot gas around galaxy clusters and keep that gas from cooling efficiently. Both modes help regulate galactic ecosystems. Without such feedback, many simulations produce galaxies that become too massive and form too many stars too quickly. Add black hole feedback, and the virtual universe begins to resemble the real one more closely. Sometimes the best proof of influence is what goes wrong when it is removed. Let us visit our own home system. At the centre of the Milky Way lies Sagittarius A star, containing about 4 million solar masses. It is comparatively quiet today, nibbling rather than feasting. Yet evidence suggests it may have been more active in the past. We know Sagittarius A star exists because astronomers tracked stars orbiting an apparently invisible central mass with extraordinary speed. Work by researchers including Andrea Ghez and Reinhard Genzel helped establish this convincingly, earning a share of the Nobel Prize in Physics. When stars whip around something unseen at thousands of kilometers per second, suspicion is reasonable. In 2022, the Event Horizon Telescope collaboration released an image of the shadow of Sagittarius A star, following its earlier image of the black hole in Messier 87. Humanity had effectively photographed the silhouette of gravity itself under extreme conditions, not bad for a species that still misplaces charges. Now let us return to galaxy formation more broadly. During mergers, gas can be funneled toward galactic centers. This inflow can feed black holes rapidly, triggering quasar phases. Two merging galaxies may each bring central black holes, which eventually sink toward the new center and form binaries before coalescing. Thus, galaxy collisions often awaken central engines. Meanwhile, the energy released can blow gas outward in galaxy-scale winds. Observations show some active galaxies ejecting material at astonishing rates. This can quench star formation by depriving the galaxy of cool gas. Paradoxically, black holes can also sometimes compress gas locally and trigger star formation in certain environments. They are not one-note destroyers. They are regulators with varied methods. This helps explain why some massive galaxies become red and dead, containing old stars with little new star formation. If gas is heated or expelled repeatedly, the stellar population ages without substantial replenishment. The lights stay on. Few new bulbs are installed. In clusters of galaxies, central supermassive black holes can prevent surrounding hot gas from cooling into enormous star-forming floods. Jets carve cavities visible in X-ray observations. These bubbles rise through intra-cluster gas, distributing energy. A compact central engine can therefore influence matter across distances vastly larger than itself. That scale mismatch remains one of the most fascinating features of black hole astrophysics. Tiny center, huge consequences. There is also the matter of timing. Many galaxies likely cycle through active and quiet phases. A black hole may spend long periods relatively calm, then become active when new gas arrives through mergers, bars, or internal instabilities. Activity can flare, subside, and return later. Galactic centers have seasons. Some are simply longer than civilizations. One might ask whether black holes are necessary for galaxies. Small galaxies can exist with modest, or perhaps no confirmed central supermassive black holes. The relationship is strongest among larger systems. But for many substantial galaxies, especially massive ones, central black holes appear deeply entwined with evolution. Not mandatory everywhere, highly relevant often. There is something philosophically striking here. In the visible imagination, stars feel like the heroes of galaxies because they shine. Yet a dark object in the center, silent most of the time, can steer the fate of billions of stars indirectly. The universe seems fond of hidden leverage. Roots hold trees, cause power planets, invisible matter shapes galaxies, dark centers regulate stellar cities, patterns repeat, and still, black holes are not tyrants controlling every detail. They are participants in a network of gravity, gas dynamics, mergers, dark matter, stellar feedback, angular momentum, and cosmic environment. Galaxy formation is too rich for single-cause stories. Even the most dramatic object must collaborate with circumstance. As observations improve, especially with facilities like the James Webb Space Telescope and future gravitational wave observatories, we will learn more about how the first black hole seeds formed and how quickly they grew. Some of the biggest puzzles in modern astrophysics live there. How did giant black holes appear so early? How often did seeds merge? How strongly did they suppress star formation? How common are hidden intermediate stages? Excellent questions for a species with insomnia and telescopes. For our purposes tonight, one truth is enough to carry forward. Galaxies are not only collections of stars, many are systems organized around a central absence so dense that it can shape everything nearby. A strange arrangement, certainly. Yet the cosmos often builds with contrasts. Light around darkness, order from collisions, life from stellar death. Stand beneath a clear night sky and everything appears calm. Stars seem fixed. Constellations hold their places. The Milky Way arches quietly overhead when conditions allow. Even distant galaxies in telescope images often look like still photographs, elegant islands frozen in black space. Yet almost nothing in the universe is truly still. Galaxies rotate, merge, feed black holes, form stars, lose gas, reshape themselves, and drift through expanding space. Entire clusters move, dark matter structures grow, light crosses billions of years before reaching us. The reason the cosmos can look peaceful is not because it lacks motion, it is because cosmic time is slow. Tonight we arrive at one of the most beautiful advantages humans possess. Although we live briefly, the speed of light allows us to see deep time directly. We cannot watch a single galaxy evolve from birth to maturity in one human lifetime, but we can look farther away and observe younger versions of the universe. Distance becomes history. This idea is so important that it deserves a moment of comfort and clarity. Light does not travel instantly. It moves at about 299,792 kilometers per second in vacuum. Very fast by ordinary standards. Slow enough, however, that space preserves the past. Moonlight takes a little over 1 second to reach Earth. Sunlight takes about 8 minutes. Light from Andromeda Galaxy takes roughly 2.5 million years. If we observe a galaxy 10 billion light-years away, we do not see it as it is now. We see it as it was when that light began its journey. Telescopes are therefore time machines, though with one notable limitation: they only travel backward. This means astronomers reconstruct galaxy evolution not by waiting for one galaxy to change before our eyes, but by comparing many galaxies at different distances, and therefore different ages of the universe. Nearby galaxies show mature stages. More distant galaxies reveal adolescence. Extremely distant galaxies reveal infancy. Put enough of these snapshots together, and a timeline emerges. That is how we learned so much about galaxy formation long before we could directly glimpse the earlier systems clearly. But in recent years, a new observatory has changed what is possible: James Webb Space Telescope. When Webb launched, many hoped it would push our view deeper into cosmic dawn, the era when the first galaxies formed. It was designed especially well for this task because the earliest visible light from ancient galaxies has been stretched by cosmic expansion into infrared wavelengths. This stretching is called redshift. As space expands, light waves travelling through it are stretched to longer wavelengths. The more distant and ancient the source, the greater the redshift generally observed. So many of the first galaxies are not best studied in visible light at all. Their once ultraviolet and visible emissions arrive to us in infrared. Webb was built to see infrared with extraordinary sensitivity. In practical terms, it is an ideal historian of the early universe, and what it has been revealing right now is both exciting and, in some cases, surprising. Let us begin with the simplest headline. Galaxies appeared early, very early. Soon after Webb began science operations, observations identified candidate galaxies from when the universe was only a few 100 million years old. Some of these systems appeared brighter, more massive, or more developed than many astronomers had cautiously expected. This did not mean the laws of physics collapsed in embarrassment. It meant models needed refinement, assumptions required testing, and the early universe may have been especially efficient at building luminous systems. Science calls this progress. Public headlines sometimes call it panic. We shall remain with science. Why was this surprising? Earlier instruments such as Hubble Space Telescope had already discovered distant young galaxies, but Webb's larger mirror and infrared power let it see fainter and farther. Once the curtain moved back, researchers found that the first billion years of cosmic history may have been busier than many expected. Star formation in some young galaxies was vigorous. Structures assembled quickly. Chemical enrichment may have advanced rapidly. Black hole growth may have begun sooner than anticipated. In short, the early universe does not seem lazy. Now, some early claims based on initial photometric estimates were later refined after spectroscopy, which is normal and healthy in astronomy. And determining precise distances and properties of very distant galaxies is difficult work. First impressions can shift when better data arrives. Even so, the broad result remains powerful. Webb is showing a rich population of galaxies in the cosmic dawn era. Let us talk about what these galaxies look like. Many are compact, some are clumpy. Some show irregular or disturbed shapes, matching expectations for systems still assembling through rapid star formation and mergers. Others seem surprisingly structured, hinting that disks or ordered components may emerge earlier than once assumed in at least some cases. That is a recurring theme in galaxy studies. Nature enjoys doing several things at once. Some young galaxies are messy, some are unexpectedly mature, some are small but intense, some are growing fast. There is no single universal childhood. Webb is also detecting heavy elements in surprisingly early galaxies. Remember, the first universe contained mostly hydrogen and helium. Heavier elements had to be forged inside stars and dispersed through stellar winds and supernova. So when astronomers find oxygen, carbon, or other metals in early galaxies, it means stars had already formed, lived, died, and enriched the gas by that time. Chemical history was underway quickly. This matters because metals help gas cool, fragment, and form later generations of stars. They are part of the transition from primitive cosmic matter to complex astrophysical ecosystems. Webb is, in effect, catching chemistry becoming interesting. Another major area of discovery involves black holes. Some very distant galaxies seem to host active central black holes earlier than expected. This raises questions we discussed before. How did supermassive black hole seeds form, and how did they grow so rapidly? Several possibilities remain under study. Perhaps some seeds were already massive through direct collapse. Perhaps accretion rates were high and sustained. Perhaps mergers accelerated growth. Perhaps several channels operated together. The universe is under no obligation to choose one neat explanation. Webb is giving us new evidence, not final closure. Now let us pause on method, because this itself is astonishing. Astronomers can analyze faint infrared light that traveled more than 13 billion years, separate it into spectra, identify chemical signatures, estimate masses, infer star formation rates, and reconstruct what galaxies were doing when Earth did not yet exist. That sentence should never become ordinary. Humanity, a species that occasionally burns toast, has learned to read ancient photons. Redshift is central to this reading. When astronomers measure a galaxy's redshift, they estimate how much the universe expanded while the light travelled. Higher redshift usually means earlier cosmic times. Webb has confirmed galaxies at redshifts corresponding to astonishingly young ages of the universe. These numbers matter because they anchor chronology. Without them, distant objects are pretty mysteries. With them, they become dated chapters in cosmic history. There is also something emotionally satisfying about how this works. We cannot visit the first galaxies. We cannot rewind the sky physically. Yet the universe preserved records in transit. Ancient light still arrives on schedule. Every night the cosmos sends archives. Webb simply has the right library card. Of course, not everything Webb sees overturns previous understanding. Much of what it reveals strengthens the broad framework already built over decades. Galaxies grow hierarchically. Early systems are often smaller and more active. Star formation peaks and changes over time. Mergers matter. Gas inflow matters. Dark matter scaffolding matters. What Webb is doing is sharpening resolution, extending reach, and exposing the details hidden behind older limits. This is often how science advances, not by replacing every old idea dramatically, but by improving clarity until finer truths emerge. Some observations also challenge researchers to improve simulations. Computer models must reproduce the number, brightness, masses, chemical properties, and shapes of galaxies across time. If Webb finds more rapid early assembly than expected, theorists adjust assumptions about star formation efficiency, feedback, gas inflow, dust, and black hole growth. Then models improve, then observations improve again. Then everyone politely bothers each other for decades. It is an excellent system. Now imagine what time slows down means observationally. A galaxy billions of light years away may be changing rapidly in its own local era, forming stars, merging, driving winds. Yet to us it appears frozen because we receive one thin slice of emitted light. We see a moment held still. Every telescope image is a paused frame. Astronomers create motion, not by watching one galaxy speedrun evolution, but by comparing many frames from many distances. Nearby spirals show later adulthood. Intermediate redshift galaxies show busier Middle Ages. Very distant Webb galaxies show early youth. Stack those snapshots mentally and cosmic cinema begins. There is humility in this method too. We never see the whole story of any one distant galaxy at once. We infer, we compare, we test, we refine. Knowledge grows through patient accumulation, much like galaxies themselves. And what about our own place in this timeline? The Milky Way did not yet look like it does now when those first Webb galaxies emitted their light. Our galaxy was still assembling from smaller structures, gathering gas, forming ancient stars, merging with companions, building the long ancestry that would eventually include the Sun. So when Webb observes first galaxies, it is not looking at strangers only, it is looking at cousins from our family's early generations. That perspective can make the night sky feel more intimate. Distant ancient galaxies are not decorative background objects. They're evidence of how systems like ours began, and Webb is not finished. Future observations will map larger samples, detect fainter systems, improve spectroscopic conformations, study dust and gas in greater detail, and trace how the first starlight reionized the universe. Some surprises are almost guaranteed. Precision usually reveals complexity. Step far enough back from any single galaxy, and even the grandest spiral begins to look small. That can be difficult to appreciate. A galaxy may contain hundreds of billions of stars, span tens of thousands of light years, host black holes, nebulae, clusters, planets, and enough matter to humble every earthly measuring habit. Yet on larger scales, galaxies themselves become building blocks in an even greater pattern. They are not scattered randomly through space. They belong to a vast structure known as the cosmic web. This is one of the most extraordinary discoveries in modern cosmology. If you could map the positions of millions of galaxies across immense distances, you would not find an even sprinkle, like sugar on a table. Nor would you find isolated islands with nothing connecting them. Instead, galaxies gather along filaments, chains, sheets, and knots, separated by enormous emptier regions called voids. The universe, on its largest scales, resembles a network, a web, a foam, a branching river basin. A nervous system, if one is feeling metaphorical but not too committed to it. Different comparisons capture part of the truth. None fully contain it. What matters most is this. Galaxies form and evolve inside a larger architecture shaped by gravity, dark matter, and time. To understand how the cosmic web emerged, we return again to those tiny fluctuations in the early universe. Regions that were slightly denser than average pulled in more matter over billions of years. Regions slightly emptier than average lost matter by comparison. As gravity amplified those differences, dense zones became denser, sparse zones became emptier. Matter did not collapse into one giant central lump because the initial fluctuations existed across many scales and locations. Instead, countless regions grew simultaneously. Filaments formed where matter streamed between dense nodes. Nodes became clusters and superclusters. Voids expanded between them. The result is the web we observe today. Dark matter plays the leading structural role here. Because it dominates much of the mass budget, its gravitational collapse largely determines where ordinary matter later collects. Gas falls into dark matter filaments and halos. Stars form in those halos. Galaxies light up the skeleton. Visible galaxies are, in a sense, the glowing skin of a darker framework. That is one of the universe's favourite habits, hiding foundations beneath brightness. Imagine rainwater gathering along cracks in pavement after a storm. Water reveals patterns that were already guiding flow. Galaxies do something similar. They mark where gravity has been channeling matter for billions of years. Now let's talk about scale, because cosmic web scale tends to make human intuition quietly resign. A single filament can stretch hundreds of millions of light years. Clusters at filament intersections may contain hundreds or thousands of galaxies bound together. Voids between structures can span tens to hundreds of millions of light years, with relatively few galaxies inside. Even galaxy clusters, themselves enormous, are only nodes in something larger. If Earth were a grain of sand, the analogy would still likely feel too modest. One nearby example of a cluster environment is the Virgo cluster, home to many galaxies including Messier 87. Our own local group, which includes the Milky Way, Andromeda Galaxy, and dozens of smaller galaxies, is part of a broader arrangement connected into larger regional structures. We do not live in cosmic isolation. We live in layers of membership. Planet within solar system within galaxy, galaxy within group, group within larger structures within the web. The hierarchy continues until scales become so large that the universe appears statistically uniform on average. Locally clumpy, globally smooth enough. That combination is deeply elegant. Now, why does the cosmic web matter for galaxy formation? Because environment shapes destiny. A galaxy forming at a filament intersection may receive abundant gas inflow, frequent mergers, and interactions with neighbours. This can accelerate growth. Massive clusters arise where matter supply has been richest. Giant elliptical galaxies often live in dense nodes, with long histories of mergers and stripping. By contrast, a galaxy in a quieter filament or near the edge of a void may experience fewer encounters and gentler evolution. It may retain gas-rich disks longer and preserve spiral structure more easily. Location influences biography. The same laws apply everywhere, but circumstances differ. This is true in forests, cities, ecosystems, and apparently the universe. Filaments also function as supply routes. Gas flows along them toward halos and clusters. Simulations suggest galaxies can be fed by streams of relatively cool gas travelling through the web, especially in earlier epochs. This fresh fuel supports star formation and growth. So galaxies are not merely born in the web, they are nourished by it. Voids deserve attention too. They are not absolute nothingness. They contain matter, dark matter, and occasional galaxies, but at much lower densities than filaments and clusters. Galaxies in voids often evolve in comparatively isolated conditions. A void galaxy may live a quieter social life, less harassment, fewer mergers, perhaps more time to keep its disk tidy. Even emptier regions can therefore teach astronomers how environment changes evolution. How do we know the web exists? Partly through galaxy surveys, projects that map millions of galaxies in 3 dimensions by measuring positions and redshifts, reveal filaments and walls spanning immense scales. Surveys such as the Sloan Digital Sky Survey transformed our picture dramatically by showing the large-scale pattern in detail, partly through simulations. Start with early universe fluctuations measured in the cosmic microwave background, include gravity, dark matter, gas physics, and expansion, then let a virtual universe evolve. What emerges looks strikingly web-like, partly through gravitational lensing, where mass bends light. This can help trace dark matter distributions associated with large-scale structures. Independent methods agreeing is always a comforting sign in science. There is another subtle feature of the web called baryon acoustic oscillations. In the early universe, pressure waves moved through the hot plasma before atoms formed. These waves left a faint preferred scale imprinted in later galaxy distributions. Modern surveys detect this pattern statistically, using it as a cosmic ruler to study expansion history. Even ancient sound waves left marks on where galaxies gather. The universe has excellent memory. Now imagine watching the web evolve in accelerated time. Matter streams along filaments toward nodes. Clusters grow heavier. Smaller halos merge into larger systems. Galaxies fall inward, sometimes stripped of gas by hot cluster environments. Tidal forces stretch stellar streams. Voids enlarge as matter drains toward denser regions. It would look less like static architecture and more like slow weather made of galaxies. This perspective helps correct a common misconception. Space is not simply emptiness with objects placed inside. It is a dynamic stage where structure grows through motion and gravity. The cosmic web is not decorative. It is active infrastructure. For the first galaxies we discussed earlier, the web was crucial from the start. Tiny halos formed first along denser regions. Gas fed inward through filaments. Proto-galaxies merged where traffic was high. Web observations of distant galaxies, combined with simulations, increasingly connect early galaxy formation to this emerging network. The first galaxies were early tenants in a building still under construction. There is something philosophically satisfying here. Humans naturally notice local things first. Our town, our sky, our galaxy. Then science keeps widening the frame. We learn Earth is not central. The Sun is one star among many. The Milky Way is one galaxy among billions. Then even galaxies become particles in a greater pattern. Perspective keeps arriving. And yet this does not diminish us. It enriches context. We are small inside something structured enough to understand. That is a generous arrangement. The cosmic web also hints at future motion. The Milky Way and Andromeda Galaxy will merge because they share a local gravitational environment. Clusters continue evolving. Some distant structures recede beyond future visibility because cosmic expansion accelerates. The web itself changes with time. Even the largest patterns are not permanent. How did our own galaxy begin inside this network? And what chain of ancient events eventually led to the particular stellar city where Earth now quietly orbits? Long before Earth had oceans, before the Sun existed, before dinosaurs, continents, trees, or anything that would one day wonder where it came from, the galaxy we call home was only a possibility. The Milky Way did not appear fully formed with graceful spiral arms, orderly stellar neighbourhoods, and a convenient location for us somewhere in the suburbs. It had to be assembled, piece by piece, merger by merger, cloud by cloud, star by star. Like nearly everything else in cosmic history, our home began smaller, rougher, and less organised than the polished version we know now. That is comforting in its way. When we look up at the Milky Way band across a dark sky, it can seem ancient and finished, a permanent fixture painted across the heavens. Yet what we are seeing is an evolving system still carrying traces of its turbulent youth. To understand how the Milky Way began, we must return to the era when the first galaxies were forming inside dark matter, halos scattered through the young cosmic web. Our galaxy likely started not as one dominant object, but as a growing region of matter where several smaller protogalactic fragments formed and later combined. This is the standard story for large galaxies in modern cosmology. They grow hierarchically, small things first, large things later. That means the Milky Way's earliest ancestors were probably modest dwarf-like systems made of dark matter, gas, and some of the first generations of stars. These early structures formed in a shared dark matter environment that would eventually become the halo surrounding today's galaxy. Gas flowed inward from surrounding filaments. Stars formed in bursts. Small systems merged. More gas arrived. Feedback from stars stirred the medium. Over hundreds of millions and then billions of years, the future Milky Way gained mass and complexity. Our galaxy was not born in one moment. It accumulated identity. The dark matter halo came first in a broad sense. Long before the visible disk reached modern scale, an invisible gravitational envelope was gathering matter. Ordinary gas fell into this halo, heated, cooled, and gradually settled. Some stars formed early in scattered clumps and small merging systems. Those ancient stars are among the oldest stellar populations we can still observe today. Many now inhabit the galactic halo. The halo is a roughly spherical region surrounding the Milky Way's disk, containing old stars, globular clusters, and dark matter. Halo stars often have low metallicity, meaning they contain relatively few heavy elements. This suggests great age, because they formed before many generations of stellar enrichment had taken place. Some of the oldest stars in our galaxy are fossils from near the beginning. They still orbit quietly above and below the disk, carrying chemical memories older than Earth itself. That idea deserves a pause. There are stars visible through telescopes tonight whose atoms have been shining since the early universe, while every human civilization came and went in less than a blink of their existence. Now let us move to the disk, because the disk is where we live. As gas continued cooling within the growing halo, angular momentum caused much of it to settle into a rotating flattened structure. Over time, this became the galactic disk. New generations of stars formed there in increasing numbers. Rotation organized motion. Gas clouds collapsed into stellar nurseries. Spiral structure developed later through density waves, bars, and internal evolution. The disk did not appear instantly thin and elegant. Early disks were likely thicker, more turbulent, and more chaotic. Gas fractions were higher. Star formation rates were stronger. Mergers and inflows disturbed the system repeatedly. Order came gradually. The Milky Way still preserves evidence of this in what astronomers call the thick disk, a population of older stars occupying a puffier component than the younger thin disk where the Sun resides. One way to think of it is that the galaxy has layers of memory. Older stars remember rougher times. Younger stars formed after the system settled further. Mergers played a crucial role throughout this growth. Our galaxy has consumed many smaller companions. Some were fully absorbed. Others are still in the process. Their stars were stretched into streams and shells, leaving signatures astronomers can detect. One of the most important known ancient mergers is often called Gaia, Sausage, Enceladus. The name sounds less like astrophysics and more like an adventurous breakfast menu, but the event itself was serious. Roughly 8 to 11 billion years ago, the Milky Way likely merged with the sizable dwarf galaxy. This collision helped build part of the inner halo and may have heated the early disk. We know this because stars retain clues in their motions and chemistry. Thanks to the European Space Agency's Gaia spacecraft, astronomers have mapped the positions and velocities of vast numbers of stars with exquisite precision. The galaxy has become readable in motion. By tracing stellar orbits, scientists identify populations that likely arrived from past mergers, rather than forming natively in the Milky Way. It is galactic archaeology. Instead of pottery fragments, the evidence is stars. Another ongoing example is the Sagittarius dwarf spheroidal galaxy, currently being tidally disrupted as it orbits us. Its stars are stretched into streams wrapping around the Milky Way. This process shows that galaxy growth through accretion did not stop long ago. Our home is still adding small extensions. The Milky Way also has many satellite galaxies, including the Large Magellanic Cloud and Small Magellanic Cloud. These companions interact gravitationally with us and with each other. Their gas and stellar streams influence the outer halo and may eventually merge more fully with the Milky Way. So even now, our galaxy remains socially engaged. At the centre of the Milky Way lies Sagittarius, a star, containing around 4 million solar masses. It likely grew alongside the galaxy through gas inflow and mergers over cosmic time. Today it is relatively quiet, but it may have been more active in the past. A calm present does not imply a calm biography. Now let us talk about chemistry, because origins are not only structural. The first Milky Way stars formed from comparatively metal-poor gas. Later generations inherited material enriched by supernovae and stellar winds. Each cycle of star birth and death added heavier elements. Eventually the interstellar medium contained enough carbon, oxygen, silicon, iron, magnesium and other elements to build rocky planets. That includes Earth. The Sun formed about 4.6 billion years ago, long after the Milky Way itself had already existed for billions of years. By then the galaxy had undergone substantial evolution. Earlier generations of stars had enriched the gas cloud that collapsed into our solar system. This means the Sun is not an original resident. It belongs to a later wave. We arrived after much of the construction was already underway. That timing may have mattered. Too early in galactic history, heavy elements were scarcer. Planet formation of Earth-like worlds may have been less common or different. Too close to the centre, energetic environments and crowding could pose challenges. Too far out, metals may be rarer. The Sun formed in a relatively moderate outer disk neighbourhood, about 26,000 light-years from the centre, where conditions were stable enough for long biological experiments, conveniently so, and yet even the Sun has travelled enormously since birth. It has completed around 20 or so orbits of the galactic centre, depending on how counted. During that time continents moved, species evolved, civilizations rose, and the galaxy continued rotating around us without requesting attention. There is something grounding in that scale. Daily worries can coexist with a 225 million year galactic year. The Milky Way's spiral arms themselves are not fixed rigid structures made of permanently linked stars. They are patterns of enhanced density through which stars and gas move. Gas entering an arm is compressed, helping trigger star formation. Bright young stars light the pattern, then drift onward. So even the luminous lane we call home is dynamic. Nothing here is frozen. Modern astronomy is still refining details of the Milky Way's origin. How many significant mergers shaped it? How early did the bar form? How much gas arrived through cold flows versus recycled fountains? How exactly did the thick disk emerge? What role did satellites play in shaping spiral structure? Excellent questions, all of them. A galaxy containing hundreds of billions of stars is allowed some complexity. There is also an emotional pleasure in learning our home has a history rather than merely an address. We often think of home as static, but the Milky Way is a product of ancient collisions, slow settling, repeated renewal and continuing motion. We live in something that became itself, that can make the night sky feel less distant and more familial. The stars overhead are not random decoration. They are members of an old city built over ages from smaller towns. Some of the atoms in you were forged in stars born in earlier Milky Way epochs. Some may even descend from systems the Milky Way absorbed long ago. You're not only from Earth, you're from a galaxy with layers. And our galaxy story is not finished. In several billion years, the Andromeda Galaxy will merge with the Milky Way, reshaping both into a new, larger system. Future skies, if anyone is watching, will look very different. Which leads naturally to the next question. Do galaxies ever truly finish forming, or are they forever changing, gathering, colliding, fading, and becoming something else across the long patience of time? Ask when a galaxy is finished and the universe responds with a useful complication. Finished in what sense? If by finished we mean fully assembled, with no more mergers, no fresh gas, no new stars, no internal rearrangement, no black hole growth, no tidal encounters, no aging of stellar populations, and no future changes of any kind, then most galaxies are never truly finished, while the cosmos still gives them time to evolve. Galaxies are not statues. They are histories in motion. That can be easy to forget because astronomy often presents galaxies as objects. We label them, photograph them, classify them, compare their masses and shapes, and place them neatly into catalogues. Spiral, elliptical, irregular, active, quiescent, barred, dwarf, giant. Useful categories, certainly. but categories can make living processes look still. A galaxy is better understood as an ongoing conversation between gravity, gas, stars, dark matter, black holes, environment, and time. Some conversations become quiet, some remain dramatic, very few end abruptly. So tonight, let us ask honestly, does galaxy formation ever really end? The short answer is no, not in one clean universal moment. The longer answer is more interesting. Consider star formation first. Many people instinctively associate a galaxy's growth with making new stars. That is sensible. Stars add visible structure, enrich gas chemically, produce planets, and illuminate the system. Yet galaxies can continue evolving even after star formation slows or stops. Some galaxies, especially gas-rich spirals like the Milky Way, still form stars today. The Milky Way creates new stars at a modest rate, perhaps around 1 to a few solar masses per year depending on method and epoch. Giant molecular clouds collapse, stellar nurseries glow, massive young stars switch on. The process continues. We live in a galaxy still under light maintenance. Other galaxies, particularly many ellipticals, formed most of their stars long ago and now appear comparatively quiet. Their stellar populations are older and redder. Cold gas is scarce. New star formation is weak. Astronomers sometimes call such systems quenched, meaning the fuel for making many fresh stars has been reduced, heated, removed, or otherwise suppressed. Does that mean they are finished? Not exactly. Even a quenched galaxy can merge with companions, accrete stars from satellites, feed a central black hole, undergo tidal interactions, or change structure through internal dynamics. Its stars continue aging, stellar remnants accumulate, orbits evolve slowly, outer halos grow through minor mergers. The lights may dim, the architecture still changes. This distinction matters because galaxy formation is not only about forming stars, it is also about assembling mass and redistributing matter. Let us talk about mergers, one of the universe's favourite tools. Large galaxies often continue growing by absorbing smaller ones. A dwarf galaxy falls inward, is stretched by tides, and eventually contributes stars, gas, and dark matter to the larger host. This can happen long after the host's main star-forming youth has passed. The Milky Way is doing this now with the Sagittarius dwarf spheroidal galaxy, whose stars are being drawn into streams around us. So even in middle age, galaxies can keep adding chapters. Major mergers between comparable galaxies can be even more transformative. A future collision with the Andromeda galaxy in several billion years is expected to reshape both spirals into a larger remnant galaxy. If galaxy formation ended once a spiral looked picturesque, that future event would be awkwardly off schedule. Clearly the cosmos does not stop at visual satisfaction. Gas accretion is another continuing pathway. Galaxies can draw in fresh material from surrounding environments or recycle gas previously expelled by stellar winds and supernovae. This inflow can reignite star formation or sustain low ongoing rates for billions of years. Some galaxies experience bursts of renewed activity after long quieter intervals. Apparently galaxies too can have second acts. Internal evolution matters as well. Bars can form in disks and funnel gas towards centres. Spiral patterns can grow and fade. Stellar migration can move stars inward or outward across disks over time. Thick disks may evolve from heating processes. Central bulges can build gradually through secular evolution, meaning slow internal change rather than dramatic mergers. A galaxy can reorganize furniture without moving house. Now let us widen the lens to cosmic time. The universe is expanding, and that expansion is accelerating due to what we call dark energy. Over immense timescales, this affects galaxy growth profoundly. Nearby gravitationally bound systems like galaxy groups and clusters can still merge internally, but distant unbound galaxies recede ever faster. Eventually, many galaxies beyond local structures will move beyond observable reach. Fresh mergers from afar become rarer. cosmic supply chains thin out. In that far future, galaxies within local bound groups may continue combining, while the wider universe becomes increasingly isolated. For the local group, the major story ahead is the Milky Way-Andromeda merger, plus subsequent interactions with smaller companions. Over trillions of years, these systems may settle into one large elliptical-like galaxy, sometimes nicknamed Milkomeda, though the name still sounds like a beverage experiment. Will that final remnant be finished? Again, not completely. Stars will continue evolving. Red dwarfs may burn for trillions of years. White dwarfs cool. Stellar encounters slowly alter orbits. Black holes merge or wander inward. Rare new stars might still form if residual gas remains. Dynamical relaxation continues. The pace slows enormously. Change does not vanish. There is also the concept of the stellar era, the vast span when stars still shine. During much of this era, galaxies remain recognizable homes of stars and remnants. Far beyond that lie even stranger futures involving degenerate remnants, black hole evaporation, and timescales so large they make current cosmology feel like weather forecasts. By then, asking whether galaxy formation ended may feel less urgent than asking whether clocks still mean anything. But for practical astronomy, the answer remains that galaxies evolve for as long as physics allows meaningful processes to continue. Now let us return to the present, because there is a subtle beauty here. Human beings often look for finished states. We imagine careers completed, buildings completed, projects completed, identities completed. Nature frequently prefers ongoing states instead. Forests are never finished. They grow, burn, recover, shift species and age. Coastlines are never finished. They erode, rebuild, flood and reshape. Galaxies are never finished. They assemble, rotate, merge, quench, revive and drift. Completion is often a human scheduling concept. The universe favours continuity. That perspective can also change how we view galaxy types. A spiral galaxy is not the final reward for successful matter. It is one temporary configuration. An elliptical is not the graveyard of a failed spiral. It is another phase shaped by mergers and environment. Irregular galaxies are not mistakes. They are legitimate outcomes of conditions and history. There is no single perfect endpoint, only trajectories. Astronomers see this in observations across redshift. Young galaxies are clumpier and more turbulent on average. Intermediate-age galaxies show growing disks and evolving populations. Nearby galaxies reveal mature structures and quieter star formation in many cases. Yet even now interactions, active nuclei and starbursts continue. The movie has slowed, it has not stopped. What about our own home specifically? The Milky Way still forms stars, still interacts with satellites, still rotates, still redistributes gas, still hosts a central black hole, still migrates stars through its disk, and still moves toward Andromeda. You currently reside inside an unfinished galaxy. That may be one of the more delightful real estate facts available. There is humility in this. We often imagine ourselves arriving late to cosmic history after the important construction is done, yet much remains underway. The sky above is not a museum ceiling. It is an active system caught mid-process, and there is comfort in it too. If galaxies billions of years old are still becoming themselves, perhaps gradualness is not failure. Somewhere above you tonight, beyond weather, beyond city glow, beyond the thin blue layer of air that keeps us comfortable enough to ask impossible questions, the universe is continuing without pause. Stars are being born inside cold clouds of gas. Other stars are dying and returning their elements to space. Galaxies are rotating through darkness. Small galaxies are falling toward larger ones. Black holes are feeding quietly in distant centers. Light that began traveling before Earth existed is still on its way, and all of it is happening while this moment, your moment, passes gently through the night. We began our journey asking what really happens when galaxies first form. At first, the answer may have sounded like something simple. Matter gathers, stars ignite, a galaxy appears. But the real story, as it so often is, turned out richer than the summary. We found a young universe that was nearly smooth, but not perfectly so. Tiny fluctuations in density became the first seeds of future structure. Gravity, patient beyond measure, amplified those slight differences over immense time. Dark matter assembled hidden frameworks. Hydrogen gas flowed inward. Clouds cooled and collapsed. Then the first stars switched on. Those early stars brought new light to a dark cosmos. They forged heavier elements. They exploded. They enriched gas for later generations. Proto-galaxies emerged from turbulence. Mergers built larger systems. Rotation organized disks. Some galaxies became spirals, some ellipticals, some irregular, and gloriously unconcerned with symmetry. At many centers, black holes grew and helped regulate the cities of stars around them. And when we stepped back far enough, we saw galaxies themselves woven into the cosmic web, connected across distances so large that even imagination needs a short rest. Then we came home. We looked at the Milky Way not as background scenery, but as a product of ancient collisions, steady inflow, chemical inheritance, and time. We realized the sun formed late in that story, from enriched gas shaped by generations of earlier stars. Which means Earth, oceans, forests, animals, cities, memory, music, and you arrived not at the beginning of galactic history, but as a later chapter written by countless earlier events. There is something deeply calming in that. You do not live beside cosmic history. You live inside it. Even now, the galaxy beneath your feet, though we rarely think of it that way, is turning. The sun carries Earth around the galactic center at extraordinary speed. The Milky Way moves through the local group. Andromeda Galaxy is drawing nearer over billions of years. Stars migrate through the disk. New stellar nurseries glow unseen behind dust clouds. Stillness, it turns out, is often motion experienced from the inside. That may be true in more than astronomy. We sometimes imagine the universe as complete because the night sky appears finished. We imagine galaxies as settled because telescope images capture a single frame. We imagine ourselves as late arrivals because the cosmos is old. Yet age and completion are not the same thing. The universe is ancient, yes, it is also unfinished. Galaxies continue forming stars. Clusters continue evolving. Black holes continue growing. Space continues expanding. New futures continue arriving. Even the largest structures are temporary arrangements in a longer unfolding. This can feel smalling at first, but I think it can also feel kind. If the stars are not finished, perhaps nothing living needs to be finished either. If galaxies require billions of years to become themselves, then gradualness may be one of nature's most common methods. If order can emerge from chaos repeatedly, then slow progress is not an exception. It is a pattern. Now imagine, just for a quiet moment, the first faint fluctuations in the young universe. Differences so tiny they would have seemed meaningless to any hurried observer. Yet from them came galaxies, stars, planets, chemistry, oceans, and minds capable of wondering where galaxies came from. Small beginnings, long patience, unexpected beauty. The cosmos seems rather fond of that formula, and perhaps tonight, as sleep approaches, there is comfort in knowing that you are made from a universe that builds gently but persistently. The calcium in your bones, the iron in your blood, the oxygen in your breath, the carbon in your cells, all were assembled through long chains of stellar and galactic change. You're not separate from cosmic evolution. You're one of its present expressions. Somewhere far away, a young galaxy is forming stars for the first time. Somewhere else, an old galaxy is fading into quiet red light. Somewhere, two spirals are beginning the slow approach that will one day reshape them both. Somewhere, photons launched before the Milky Way had its current former crossing emptiness toward future eyes. And here, in this room, on this world, in this turning galaxy, you have reached the end of our journey for tonight. So let your breathing settle. Let the day loosen. Let the mind drift if it wishes. The universe will continue its patient work without needing supervision. Thank you for spending this time with Science for Sleep. If this journey brought you some calm, some wonder, or simply a softer landing into the night, I'm glad you are here. Rest well, and while you sleep, everything keeps becoming.